Imagine a civilization so advanced that it can build colossal structures around stars, capturing their energy and using it for unimaginable purposes. This is not the realm of science fiction. It's a concept proposed by one of the most brilliant minds of the 20th century. A visionary physicist, Freeman Dyson, envisioned a megastructure capable of enveloping a star, capturing its vast amounts of energy. This idea, while radical, is rooted in the basic principles of energy consumption and technological progress. But why would an advanced civilization need such a structure? As our civilization advances, our energy needs grow exponentially. But our most ambitious projects pale in comparison to the energy output of our Sun, which releases more energy in 1 second than humanity has consumed in its entire history. Imagine harvesting every bit of a star's energy, turning it into a power plant with nearly limitless potential. If realized, this colossal undertaking would revolutionize how we think about energy and its possibilities. But what would such a structure look like? And even more intriguingly, how would we be able to detect it from our distant vantage point here on Earth? The problem lies in our ability to detect signs of such advanced engineering. While we are just beginning to tap into our planet's energy resources, discovering such an advanced civilization is exciting and frightening. Recent research has revealed unusual infrared signals from 7 distant stars, sparking debate and fueling imagination. Could these signals be techno-signatures? Either way, these anomalies defy natural explanations. What's behind these mysterious infrared glows? Are they evidence of advanced extraterrestrial engineering or natural phenomena that we've yet to understand? To understand the concept of Dyson spheres, we must first familiarize ourselves with the Kardashev scale, a method of measuring a civilization's level of technological development based on its energy consumption. In 1964, Soviet astrophysicist Nikolai Kardashev proposed this scale, dividing civilizations into 3 types, depending on their energy consumption. Type 1 civilizations use all the energy available on their home planet, including geothermal, solar, wind, and other natural energy sources. Imagine controlling the power of earthquakes and volcanoes to power our cities. This is the hallmark of a Type 1 civilization. Civilizations of the second type go even further, receiving energy directly from their star. This is where the Dyson spheres comes into play. By surrounding their star with massive structures, these civilizations can use almost all of its energy. Type 3 civilizations, in turn, are even more advanced and can harvest and harness the energy of their entire galaxy. They control the energy of billions of stars, making them unimaginably powerful. The relevance of the Kardashev scale to Dyson spheres lies in the connection between energy consumption and technological progress. As civilizations evolve, their energy needs grow exponentially, forcing them to develop ever more ambitious methods of meeting those needs. But how can we discover the Dyson sphere? One of the most significant milestones in cosmic observation, the development of infrared astronomy, can help us in this challenging endeavor. Infrared astronomy allows us to see the universe in a new light, literally. By observing the infrared spectrum, scientists can detect heat emitted by celestial objects and reveal details invisible to traditional telescopes. This capability has played a crucial role in the search for techno-signatures, signs of advanced civilizations beyond Earth. This journey began in the mid-20th century, when astronomers used infrared sensors to study space. These early works laid the groundwork for today's sophisticated infrared observatories, such as the Wide Field Infrared Survey Explorer, WISE, and the James Webb Space Telescope. These instruments have opened a new frontier in astronomy, allowing us to detect faint thermal signals from distant stars and galaxies. But what does this have to do with the search for Dyson spheres? Well, in the 60s, theoretical physicist Freeman Dyson proposed an audacious idea. An advanced civilization could build a massive structure around its star to capture its energy. He envisioned a swarm of solar collectors or habitats orbiting the star and forming what we now call a Dyson sphere. But how could it possibly be detected if it blocked the light of its star? Of course, such a structure would emit vast amounts of infrared radiation, making it visible even from Earth. Dyson's hypothesis was more than just a thought experiment. It provided a viable way to search for intelligent extraterrestrial life. By surveying the excess infrared radiation around stars, we could find evidence for the existence of these colossal structures. This concept led scientists to the recent discovery of several stars with unusual infrared emission. Modern infrared astronomy opens new horizons in the search for Dyson spheres and other technosignatures. By observing the universe in the infrared wavelength range, we can detect thermal emission from celestial objects, allowing us to understand phenomena invisible to traditional optical telescopes. One of the most important instruments in this work is the Wide Field Infrared Survey Explorer. Launched in 2009, WISE has revolutionized our understanding of the infrared universe. Its mission is to map the entire sky in infrared light, revealing countless celestial objects, including stars, galaxies, and asteroids. This is a mosaic of the images covering the entire sky, as observed by the WISE, part of its all-sky data release. WISE's ability to detect excess infrared emission around stars plays an essential role in the search for Dyson spheres. By analyzing the heat signatures recorded by WISE, scientists can identify stars with unusual infrared emission, which may indicate the presence of advanced megastructures. One prominent example is the Hephaistos project, led by a team from Uppsala University. This ambitious initiative aims to identify potential candidate Dyson spheres by analyzing Gaia, 2-mass, and WISE data. Hephaistos uses a sophisticated system to sift through millions of stars in search of those with excess infrared emission that natural phenomena cannot easily explain. The project uses machine learning algorithms, including convolutional neural networks, to weed out false positives and identify the most promising candidates. The project's methodology is rigorous. It begins by collecting data from several sources, including precise measurements of the position and distance of the stars using Gaia, near-infrared 2-mass observations, and mid-infrared WISE data. This comprehensive dataset allows the team to create detailed models of potential Dyson spheres. The team then uses a grid search method to compare the observed data with theoretical models. This involves calculating the expected infrared emission for different configurations and temperatures of Dyson spheres, and then comparing these models to the observed infrared excess. Through this careful process, Hephaistos has identified 7 potential candidates for a Dyson sphere. All of these objects are M-dwarfs, stars known for their relatively low luminosity, making the detection of infrared excess even more intriguing. These findings are significant because they demonstrate the potential for using long-standing astronomical data for such detections. The quest to detect Dyson spheres and other technosigns is driven by ongoing advances in infrared astronomy. These innovations allow us to explore the universe with unprecedented precision and detail. One of the most significant breakthroughs in infrared astronomy is the development of adaptive optics and advanced sensors. Adaptive optic systems correct for distortions caused by the Earth's atmosphere, providing clearer and more detailed images of celestial objects. This technology is vital for isolating faint infrared signals from background noise. In addition, integrating machine learning algorithms into data analysis has revolutionized our ability to sift through vast amounts of astronomical data. These algorithms can identify subtle patterns and anomalies that may indicate the presence of technosignatures. Among the most revolutionary achievements is the James Webb Space Telescope, which has already managed to change our understanding of the cosmos in more ways than one. With its advanced infrared capabilities, the JWST allows us to look deeper into space and time than ever before. JWST's primary mirror, which is more than 16 times larger than the WISE mirror, combined with susceptible infrared instruments, can detect the faintest thermal signals from distant stars and galaxies. Essential is the telescope's ability to observe in the mid-infrared region of the spectrum. If they exist, Dyson spheres are likely to emit heat in this range, making them visible to JWST. By scanning the sky for these infrared signatures, JWST could provide compelling evidence for the existence of advanced extraterrestrial civilizations. However, its busy schedule, planned months in advance and filled with many other important research projects, limits the amount of time for searching for Dyson spheres. Radio astronomy, in addition to infrared observations, plays no small role in the search for technosigns. The Very Large Array in New Mexico is one of the world's premier radio observatories, capable of detecting radio waves across the universe. Radio waves can provide important information about the presence and nature of technosignatures. For example, a Dyson sphere may emit infrared radiation and radio signals as a byproduct of energy harvesting processes. VLA can detect these signals, offering a different but complementary perspective to infrared observations. Developing and implementing advanced technologies will only improve our ability to find technosignatures. However, the results of the team from the Uppsala University are not isolated. Another recent study entitled A Data-Driven Search for Mid-Infrared Excesses Among 5 Million Main Sequence FGK Stars by Gabriela Contardo and David W. Hogg found 53 stars with significant infrared excesses. This large-scale search also used Gaia, DR3, 2MASS, and WISE data to detect anomalies in the mid-infrared range. The technique involved training machine learning models to predict expected infrared magnitudes based on other stellar characteristics. Stars in some bands appeared significantly brighter than predicted, and thus were flagged as potential candidates. After applying additional filters to help avoid false positives, the study narrowed the 4.9 million sample to 53 stars. Analysis of these findings reveals several intriguing candidates. For example, one of the identified stars shows an infrared excess consistent with extreme debris disk characteristics, which could be mistaken for a technosignature. However, its older age calls into question existing models of planet formation, suggesting either an extended disk evolution or alternative processes. The implications of these discoveries are profound. If any of these infrared anomalies are indeed Dyson spheres, it would provide direct evidence of the existence of advanced extraterrestrial civilizations. However, the scientific community remains cautious. Natural phenomena such as dust clouds or the extreme debris disk can also provide similar infrared signatures. Therefore, each candidate requires careful follow-up observations to confirm or deny the presence of artificial structures. The controversy surrounding these findings emphasizes the difficulty distinguishing between natural and artificial sources of excess infrared radiation. Indeed, in general, the vast distances between Earth and potential candidates pose a severe problem. Many of the stars under study are thousands of light years away, making detecting and analyzing their infrared signatures extremely difficult. The farther away a star is, the fainter its signals are, and the harder it is to obtain good quality, accurate data. Some scientists argue that our current understanding of stellar and planetary dynamics is incomplete, and these anomalies may reveal new astrophysical phenomena rather than technosignatures. The search for extraterrestrial life has gripped humanity for centuries, evolving from philosophical speculation to a rigorous scientific approach. Today, scientists use various methods to detect signs of life beyond Earth, focusing on technosignatures and biosignatures. While technosignatures are indicators of advanced technological activity, including large-scale structures like Dyson spheres, unusual energy emissions, or artificial signals, biosignatures, on the other hand, are indicators of biological activity. They can range from detecting specific gases in a planet's atmosphere, such as oxygen and methane, to surface features indicative of life. Current and upcoming missions are crucial in detecting these subtle signs of life. For example, the James Webb Space Telescope can observe in the infrared, detecting the faint heat signatures of distant exoplanets and their atmospheres. This provides valuable data on potential conditions suitable for life. It has confirmed dozens of potentially habitable exoplanets in the past year alone. Another important initiative that goes shoulder to shoulder with JWST is TESS, the Transiting Exoplanet Survey Satellite, which aims to detect exoplanets by observing their transits through stars. TESS has already identified thousands of exoplanet candidates, many prime targets for further study with more powerful telescopes, such as Webb. Future missions promise to further enhance our ability to detect technosigns and biosigns. The proposed LUVOIR, Large UV Optical IR Surveyor, and HABEX, Habitable Exoplanet Observatory missions, are designed to directly image exoplanets and analyze their atmospheres. These next-generation telescopes will provide unprecedented clarity and sensitivity, allowing us to detect even the faintest sign of life or advanced technology. In addition to space observatories, ground-based telescopes, such as the Extremely Large Telescope and Square Kilometer Array, will play a crucial role. ELT, with its massive mirror, will be able to obtain direct images of exoplanets and study their atmospheres in detail. At the same time, SKA will focus on detecting radio signals from space that could indicate technological activity. The search for life is not limited to looking for existing civilizations. Scientists are also exploring the possibility of life in our solar system, focusing on moons such as Europa and Enceladus, which have subsurface oceans. Missions such as Europa Clipper and potential future missions to Enceladus aim to detect signs of microbial life in these hidden waters. As we continually refine our methods and technologies, each discovery, whether it confirms or disproves the existence of life, brings us closer to understanding our place in the universe. The journey is as important as the destination. It pushes the boundaries of science and ignites our collective imagination. And each innovation brings us closer to answering one of humanity's deepest questions. Are we alone in the universe? Surely you've heard by now that black holes can be so massive that they can outshine entire galaxies. But some of them are quite mobile. So much so that they roam the Milky Way like cosmic ghosts, undetectable. Of course, you may be confused or even mesmerized by the fact that the nearest black hole to Earth is not as far away as you think. And when these cosmic giants collide, they generate frequencies as unique as fingerprints. Frequencies that may hold the key to unlocking the deepest mysteries of the universe. But did you know that these waves interact in a far more complex way than we ever imagined? Get ready for an extraordinary journey as we begin to delve into the mysteries of black holes, the truly enigmatic titans of the universe. In the cosmic pattern, black holes are weavers of riddles and paradoxes. Although we're familiar with small black holes, the remnants of dying stars and supermassive ones lurking in the hearts of galaxies, there is an enigmatic class that eludes our telescopic gaze: intermediate mass black holes. The Hubble Space Telescope, our eye in the sky, recently focused its attention on Messier 4, the ball cluster closest to Earth. What he discovered was nothing short of groundbreaking: a black hole with a mass about 800 times the mass of our Sun. This celestial object is somewhere between 6,000 and 7,200 light-years away from us. Why is this so important, you ask? Well, for years, astronomers have struggled with a gap in the black hole genealogical tree. We've had evidence of both small black holes, a few times the mass of our Sun, and supermassive black holes with masses in the millions or billions of solar masses. But black holes of intermediate mass turned out to be a missing link, mysterious relatives about which everyone has heard but no one has met. An equally interesting question is how these black holes of intermediate mass form. One theory suggests that they could be the nuclei of dwarf galaxies that lost their outer stars when they merged into larger galaxies. Another theory states that they could have formed from the collision and merger of smaller black holes. Identifying these elusive black holes is no easy task. It requires a symphony of scientific instruments, from X-ray observatories to precise calculations based on the motion of surrounding stars. The Hubble Space Telescope, with its unprecedented resolution, has played an important role in this discovery. The presence of a black hole affects its cosmic environment. By studying the gravitational choreography of stars orbiting this massive object, scientists have been able to estimate its mass. It's like understanding the character of an invisible puppeteer by watching the puppets dance. The discovery of intermediate mass black holes could rewrite the cosmic narrative. They may be key players in the formation of galaxies and may even hold clues to the mysterious dark matter that makes up most of the universe. In a cosmic world where distances are often incomprehensible, the term neighbor takes on new meaning. While our closest celestial neighbor, the Moon, is only 238,855 miles away, our nearest neighboring black hole, Gaia BH1, is thousands of light-years away from Earth. But what does that proximity mean in the context of black holes? And why is this proximity important? In 2020, the European Southern Observatory, ESO, made headlines when it announced the discovery of a black hole in the HR 6819 system, located just 1,000 light-years away. This would make it the closest known black hole to Earth. However, this claim was later disproved. Subsequent research by Abigail Frost of the University of Leuven in Belgium found that HR 6819 does not contain a black hole at all. Instead, it's a double star system in which one star absorbs the mass of the other, a process known as stellar vampirism. This revelation was more than just a correction. It opened up new possibilities for studying stellar evolution and interactions. After the ejection of HR 6819, the title of the closest black hole to Earth went to Gaia BH1. This black hole was discovered by the Gaia Space Observatory, a mission of the European Space Agency, ESA. The main task of Gaia is to map the Milky Way in unprecedented detail and it was thanks to this painstaking work that Gaia BH1 was discovered. As the closest known black hole to Earth, Gaia BH1 offers a unique opportunity for scientific observations and research. Its relative proximity allows for more detailed measurements and may help answer fundamental questions about the properties of black holes, such as mass, rotation, and behavior near their event horizons. The study of black holes like Gaia BH1 relies on several observational instruments, from X-ray observatories to radio telescopes. Each instrument represents a piece of the puzzle. The closer a black hole is, the more accurately these instruments will be able to measure its properties, offering a more complete picture of these mysterious objects. Beyond its scientific significance, the idea of a nearby black hole captivates the public imagination. It makes the cosmic more personal and provides a tangible focus for education and outreach. The story of Gaia BH1 can serve as a gateway for people to astronomy and astrophysics, enriching our collective understanding of the universe. In the cosmic theater, black holes often play the role of mysterious villains lurking in the centers of galaxies or double star systems. But what happens when a black hole is left to roam the universe alone, unconnected to any galaxy or star? What causes these black holes to become rogue? And how do astronomers even manage to find such elusive objects? Let's dive into the mysterious world of rogue black holes. The scientific community was ecstatic when astronomers announced the first ever unambiguous discovery of a wandering black hole. Located 5,000 light-years away from Earth, this black hole weighs 7.1 times the mass of our Sun and moves at a staggering speed of about 28 miles per second. The key to this revolutionary discovery lies in a phenomena predicted by Einstein's general theory of relativity, known as gravitational lensing. When a massive object, such as a black hole, passes in front of a background star, its intense gravitational field deflects the light of that star. This creates a brief brightening phenomena, which is how this wandering black hole was discovered. As we know, the birth of a wandering black hole is nothing short of a dramatic event. When a massive star exhausts its nuclear fuel, its core collapses, leading to a supernova explosion. The energy released can be so enormous that it ejects the newborn black hole from its stellar cradle, sending it on an endless journey through space. And this is how our newly discovered wandering black hole likely began its cosmic odyssey. What is even more intriguing is the speed at which this wandering black hole is traveling. Its speed is about 28 miles per second, which is a very large value relative to the nearest stars. This speed is likely the result of the very impact of a dying massive star, sending it on a lonely journey. The discovery of this lone black hole is just the tip of the iceberg. In upcoming missions, such as the European Space Agency's Gaia telescope and NASA's Nancy Grace Roman Space Telescope, astronomers expect to find even more such space travelers. These future discoveries will not only increase the number of known rogue black holes, but also refine our theories about their properties and frequencies. Each galaxy is like a cosmic dance floor, where stars, gas, and dust swirl in a complex choreography. At the center of this dance is a supermassive black hole that sets the rhythm and tempo of the entire galaxy. Research published in the monthly notices of the Royal Astronomical Society shows that galaxies and their central black holes grow together, regardless of their location in the universe. Astronomers have long been puzzled over the relationship between the mass of a galaxy and its central black hole. The two seem to be aware of each other, even though the black hole is much smaller than the galaxy in which it resides. This relationship implies a deep cosmic connection, a kind of cosmic codependency, where the growth of one affects the other. One of the most intriguing questions in astronomy is, which came first, the galaxy or the black hole? The answer remains elusive. What is clear, however, is that a close connection was established very quickly on a cosmic scale, paving the way for a complex interplay of growth and evolution. Let's dive into the young, gas-rich galaxies, the cradle of giant black holes. These galaxies are like cosmic nurseries, teeming with the raw materials needed for star formation and black hole growth. Studies show that such galaxies, known as blue nuggets, have exceptionally high star formation rates. They are fed by nearby gas streams, which not only accelerate star formation, but also contribute to the rapid growth of their central black holes. When black holes are fed, they become active. The gas around them heats up and emits powerful waves of radiation. This heated gas is less likely to hit the black hole, creating a feedback loop that stabilizes the size of the black hole. However, as the galaxy grows, it can push more gas toward the center, allowing the black hole to feed and grow again. The relationship between galaxies and their black holes adjusts itself. If a black hole is too large for its galaxy, it grows slower, and if it's too small, it catches up due to the abundance of gas and dust in the galaxy. So some galaxies defy the norm. These blue nuggets, despite their small size, have exceptionally large central black holes. As these galaxies age, their star formation stops and they turn into red nuggets, still retaining their huge black holes. As we move farther into the black hole abyss, it becomes apparent that young, gas-rich galaxies serve as the birthplace of various black hole phenomena. Whether they're luminous black holes or intermediate mass, wandering black holes hurtling through space, or the nearest black holes to Earth, their origins can often be traced back to these bright, young galaxies. Understanding the cradle of these cosmic giants helps us unlock the mysteries that black holes hold. Now, let's look at something really rare. There is a situation where black holes collide. In doing so, they create a cosmic symphony of gravitational waves around them that vibrate in the very fabric of space-time. These waves, first detected by the Laser Interferometer Gravitational Wave Observatory, in 2015 opened a new frontier in astronomy. However, recent research shows that these waves interact in complex ways as they propagate, thereby testing our understanding of gravity and the general theory of relativity. Traditionally, scientists have used linear models to describe these waves. However, a new study has revealed nonlinear effects that reveal a more complex picture. It's akin to the difference between a calm pond and a rough sea. In a calm pond or linear pond, the throw of a stone creates an isolated ripple. In a stormy sea, or nonlinear, however, multiple forces interact to create complex wave patterns. When black holes collide, they emit unique frequencies or chirps. These sounds are like individual notes in our cosmic symphony, each telling us something about the properties of colliding black holes. They offer a new way to test the limits of the general theory of relativity and may even provide clues to the nature of dark matter. Recent discoveries have shown that pairs of black holes and dwarf galaxies are on a collision course. These dwarf galaxies attract gas that feeds their black holes, causing them to grow even before they merge. This process is a microcosm of the larger universe, where galaxies and their central black holes grow in tandem. These colliding dwarf galaxies offer a glimpse into the early universe, which was filled with similar small galaxies. Most of these eventually merged to form larger galaxies, like our Milky Way. Understanding these processes helps us piece together the cosmic mystery of galaxy and black hole formation. As we travel deeper into the abyss of black holes, we discover that each type, from luminous black holes of intermediate mass to wandering black holes hurtling through space, plays a unique role in this great cosmic symphony. The next generation of gravitational wave detectors will likely deepen our understanding of these cosmic phenomena. And of course, each discovery, from the frequencies they generate to the nature of gravity itself, undoubtedly adds a new level to our understanding of the universe. As our telescopic eyes become sharper and computational models become more sophisticated, who knows what other cosmic mysteries these giants of the cosmos will reveal. There's an interesting mystery in our world, generated by the equations of Einstein's general theory of relativity. It's the theoretical analog of the black hole familiar to many. We call it a white hole. Imagine a region of space where, unlike an all-consuming black hole, nothing can penetrate. Instead, this cosmic anomaly defies our expectations by ejecting matter and energy, glowing violently on the dark canvas of space. In a universe governed by the concept of an arrow of time, where events flow from past to future, a white hole is a tantalizing paradox. It's like watching a space movie in reverse, where the rules of gravity and time seem to be rewritten. But are these celestial wonders just mathematical curiosities? Or do they hold the key to understanding the deeper truths of our universe? Let us delve into the mysteries of white holes, exploring their theoretical underpinnings, their enigmatic characteristics, and their potential role in the great history of the universe. In the early 20th century, Albert Einstein revolutionized our understanding of the universe by creating the general theory of relativity. This groundbreaking theory proposed a radical idea. Gravity is not a force pulling objects together, but rather a curvature of space-time caused by mass and energy. Imagine space-time as a fabric stretched like a cosmic trampoline. When an object of mass, such as a star or planet, lands on this fabric, it causes a dip. This curvature directs the motion of other objects, which move along curved trajectories in space-time. This is gravity, as Einstein envisioned it. Einstein's theory led to the prediction of black holes, regions in space where the gravitational pull is so strong that nothing, not even light, can escape. These cosmic giants form when massive stars collapse under their gravity, distorting space-time to the extreme. Introducing Carl Schwarzschild, a brilliant physicist who, while fighting in World War I, found an interesting solution to Einstein's equations. Schwarzschild's solution described space-time around a spherical, non-rotating mass, such as a star. Schwarzschild's work laid the foundation for understanding black holes, but it also hinted at something even more mysterious. If a black hole is a region from which nothing can escape, could its polar opposite exist? A region where nothing can enter, but only leave? This led to the birth of the concept of a white hole. Just as a black hole is the end point of gravitational collapse, a white hole can be thought of as a reverse black hole, a cosmic fountain ejecting matter and energy. However, unlike black holes, which have already been observed, white holes remain a theoretical concept, a tantalizing possibility in the vast cosmic mystery. In the field of astrophysics, the path from mathematical abstraction to physical reality is often long and difficult, and white holes are no exception. These theoretical entities arise from the complex equations of the general theory of relativity, the same mathematical structure that predicts the existence of black holes. The math of white holes is robust, but it's like a jigsaw puzzle with missing pieces. We understand their theoretical basis, but the real challenge is to relate these mathematical models to observable phenomena. Imagine a universe in which, instead of collapsing inward, a region of space-time does the opposite. It explosively ejects matter and energy. This is the essence of a white hole, a mirror image of a black hole, in which the flow of time and matter is reversed. But can these mathematical abstractions exist in our physical reality? The debate among scientists is ongoing and multifaceted. Some theorists suggest that white holes may be remnants of the early universe, exotic structures woven into the fabric of space-time itself. Others suggest they may represent the other end of a black hole, a kind of cosmic exit door from which matter and energy reappear after being swallowed up by the black hole. The novel idea of quantum gravity suggests that as a black hole evaporates over many epochs, losing mass, it may reach a point at which it can no longer sustain itself as a black hole. At that point, it may turn into a white hole, releasing the trapped contents back into the universe. However, there are serious problems with the physical existence of white holes. The laws of thermodynamics, especially the concept of entropy, presents a serious obstacle. Entropy, a measure of disorder, tends to increase in the universe. White holes, by their nature, decrease entropy, which contradicts this fundamental principle. Moreover, the stability of white holes is a controversial issue. Some theories suggest that if they did form, they'd be extremely unstable and would probably collapse almost instantaneously into black holes. In outer space, white holes represent one of the most enigmatic and paradoxical concepts. These mirror images of black holes have characteristics that challenge our traditional understanding of physics. Let us understand in more detail what is the concept of a white hole in theoretical physics. At the heart of a white hole is its event horizon, a boundary not of inescapability, as it is with black holes, but of impenetrability. This event horizon marks the point where matter and energy are ejected, creating a spectacle of cosmic proportions. Unlike a black hole, which takes over everything, a white hole is the source of the expulsion, the cosmic fountain from which matter and energy arise. One of the most intriguing aspects of white holes is the concept of time reversal. In the universe, time usually flows in one direction, from the past to the future. However, white holes seem to reverse this flow. It's like watching a space movie played backwards, where the usual rules of time and space are reversed. Deepening into the nature of white holes, we face a realm of paradoxes and problems. One of the most important is their connection with the previously mentioned entropy. According to the second principle of thermodynamics, entropy, or the measure of disorder, should always increase in a closed system. However, white holes seem to ignore this law, decreasing entropy and ejecting matter in an ordered state. This apparent violation of thermodynamic laws presents a serious problem for our understanding of physical processes in the universe. How can such an object as a white hole exist if it contradicts such a fundamental principle? Another paradox lies in the concept of the arrow of time. While the universe moves inexorably forward in time, white holes suggest a scenario in which time can flow backward, at least from a certain point of view. This concept breaks not only our understanding of time, but also the very nature of causality in the universe. Let us summarize the characteristics of white holes, their event horizons, the expulsion of matter, and the concept of time reversal present a fascinating but paradoxical picture for theories that, while we're looking to solve these problems, white holes remain in the realm of theoretical physics. As we delve deeper into the mysteries of the cosmos, the concept of white holes invites us to rethink our understanding of the universe. These theoretical objects are not just surprising anomalies. They may have profound cosmological implications. Consider the Big Bang, the colossal explosion that marked the beginning of our universe. Some theorists suggest that this pivotal moment in cosmic history was not just a random explosion, but that the event may have been a white hole of unimaginable magnitude, an eruption of matter and energy that gave birth to the cosmos. This view offers a radical new interpretation of the origin of our universe, suggesting that white holes may play a role in cosmic genesis. Imagine a white hole not just as a theoretical construct, but as the very source of the creation of our universe. In this scenario, the Big Bang could be envisioned as a white hole, unfathomable scale, spewing out matter, energy, and space-time that subsequently evolved into the stars, galaxies, and planets we observe today. This view offers a radical rethinking of the Big Bang. Instead of an undefined singularity, we have a white hole, an entity defined by the laws of physics albeit in a form that stretches our understanding to its limits. This white hole may have been the first spark that set the stage for subsequent cosmic evolution. If the Big Bang was indeed a white hole, it raises profound questions about the nature of our universe. What was the source of this white hole? Was it the result of a collapse of the universe from another dimension, or the result of processes beyond our current scientific understanding? This concept also changes our perception of time and causality. If the Big Bang was a white hole, it suggests the existence of a universe with a more complex timeline, in which the beginning and end of cosmic phenomena are intertwined in ways we've yet to understand. This idea of the Big Bang as a white hole organically combines with the Big Bounce theory, according to which the beginning of our universe may be the result of the collapse of the previous universe. It unites the idea of cyclical universes, suggesting that each cosmic end can give rise to a new beginning, similar to the explosive genesis of a white hole. The existence of white holes may also confirm the concept of parallel universes. If white holes can eject matter and energy, could they be a gateway to other universes? This possibility is related to the multiverse theory, which postulates the existence of multiple, possibly infinite universes, along with our own. In parallel universes, there may be different versions of physics, alternate histories, and perhaps even variations of ourselves. Another intriguing connection relates to wormholes, hypothetical tunnels in space-time. Theoretical models suggest that wormholes could link distant regions of space, and perhaps even different universes. If white holes are connected to wormholes, they could serve as cosmic portals, opening paths to remote corners of the universe or other dimensions altogether. This connection raises tantalizing questions about the nature of space and time. Could white holes and wormholes allow travel over vast cosmic distances, or even between different universes? Looking into the future of astrophysics, we see that at the moment there's a lot of scientific research in one way or another affecting the subject of white holes. But two research papers stand out among the rest, shedding light on the mysterious nature of these cosmic objects and offering new ideas and possibilities that could revolutionize our understanding of white holes. The first paper takes us on a journey to the very edge of black and white holes, exploring the close connections between them and refocusing on the physics occurring near their horizons. The authors introduce the concept of horizon-penetrating coordinate systems, a revolutionary approach that allows us to distinguish between the horizons of black and white holes. They differ from standard curvature coordinates in a small near-horizon region to emphasize the distinction between black and white horizons, which depends on near-horizon physics. This study suggests that black holes may not be the cosmic dead ends we once thought. Instead, they may be in quantum superposition with white holes, creating a scenario in which observed phenomena may hint at the existence of these theoretical white counterparts. The paper also delves into the role of quantum physics in these near-horizon regions, suggesting that quantum effects may dominate, leading to significant implications for our understanding of white holes. However, the authors emphasize that there's a problem in observational astrophysics, in which there is substantial observational evidence for black holes, but relatively weak observational support for white holes. Moving on to the second paper, titled New Black-to-White Hole Solutions with Improved Geometry and Energy Conditions, we find that the focus here is on the way to convert black holes into white holes, guided by the principles of quantum gravity. This study presents models in which the effects of quantum gravity prevent the formation of singularities inside black holes, providing a smooth transition to white holes. This solves the long-standing paradox of information loss by assuming that matter can pass through a black hole and appear in a white hole. The paper also explores geodesics within these models, confirming the completeness of particle trajectories in the transition from the black hole region to the white hole region. This supports the idea of a continuous, unimpeded flow of matter, changing our understanding of these cosmic phenomena. By integrating these theoretical developments with emerging technologies, we stand on the threshold of a new era in astrophysics. The future of white hole research promises to reveal new aspects of the universe where the boundaries between quantum mechanics and general relativity are blurring. To summarize, we can say that the future of white hole research is very bright. Who knows? Perhaps very soon we'll be able to discover indirect evidence for the existence of these intriguing objects. For years now, there's been a concept that defies the very laws of physics as we know them, a dream that has spawned countless stories and science fiction fantasies. This mystery is the search for a warp drive, a technology that could potentially allow us to travel vast distances in space faster than light itself. Imagine a journey where time and space constraints yield to the power of human ingenuity, where the farthest corners of the universe suddenly become accessible. This isn't just science fiction, it's a puzzle that scientists have been piecing together for decades, ever since physicist Miguel Alcubierre proposed a theoretical model in 1994. Alcubierre's model, a bold combination of imagination and Einstein's theories, offers a way to bend the fabric of space-time itself. But what lies behind this bold idea? Is it a mere flight of fancy? Or could it be the key to unlocking interstellar travel? Today we explore the tangled web of problems and breakthroughs surrounding warp drive. From the mysterious nature of negative energy to the tangled horizon problem. So let's dive into the depths of one of the most intriguing scientific quests of our time. The quest for the warp engine. Science or fiction? In the heart of Mexico City, amidst the hustle and bustle of city life, a young mind was fascinated by the mysteries of the cosmos. We're talking about Miguel Alcubierre. Born in 1964, a physicist whose name has become synonymous with one of the most innovative ideas in theoretical physics. His journey began in Mexico and led him to the prestigious University of Wales, where he delved deeply into the fields of general relativity and cosmology. In 1994, while working at the Max Planck Institute for Gravitational Physics in Germany, Alcubierre made a breakthrough in world perception that challenged our understanding of space travel. Inspired by the iconic science fiction series Star Trek, he posed a bold question. Could the laws of physics allow for a real warp drive? Let's break down the Alcubierre drive. Imagine a spaceship that does not move through space in the usual sense, but sits in a space-time bubble. This bubble, or deformation bubble, is the key to the Alcubierre concept. According to Einstein's general theory of relativity, massive objects distort the fabric of space-time. Alcubierre hypothesized that if we could manipulate space-time in a controlled way, we could create a warp bubble. The space in front of the bubble is compressed, pushing the bubble forward. Behind it, space expands, pushing it from behind. Inside this bubble, the spaceship remains stationary, but the bubble itself moves, allowing the ship to move faster than light without violating the laws of physics. This idea doesn't involve moving the spaceship at high speed. Rather, it's about moving space around it. It's like putting a surfboard, a spaceship, on a wave warp bubble and letting the ocean, space-time, carry it. However, the Alcubierre model is not simply a manipulation of space. It requires exotic matter with a negative energy density to stabilize the warp bubble. This exotic matter is one of the many theoretical obstacles scientists face as they try to turn the Alcubierre drive from a fascinating theory into reality. Delving deeper into the practical aspects of the Alcubierre drive, we're faced with huge challenges that stand between theory and reality. The first of these is the scale of energy and mass requirements. It was originally thought that creating a warp bubble would require an amount of energy equivalent to the mass of the observable universe, an unimaginably huge amount, far beyond our current technological capabilities. However, the field of theoretical physics is constantly evolving. An outstanding achievement was when physicist Chris Vanderbroek proposed modifications to the shape of the warp bubble. These adjustments dramatically reduce the energy requirement to about the mass of 3 suns. Still a colossal amount, but a significant step down from the original estimates. The second major obstacle is the need for exotic matter and negative energy. In the Alcubierre model, this exotic matter is crucial to stabilizing the warp bubble and making it function as intended. Negative energy is a peculiar and controversial concept. It's a concept in physics that can distort the very fabric of space-time. It's not just the absence of energy, but an actual physical quantity with negative characteristics. In the context of Alcubierre drive, negative energy will counteract the effects of normal positive energy, creating the conditions necessary for the existence and stability of the warp bubble. Negative energy, in the context of Alcubierre drive, is indeed a complex and somewhat elusive concept in physics, and it's important to distinguish it from the more familiar concepts of gravitational potential energy. In classical physics, the concept of negative energy often refers to gravitational potential energy. For example, the gravitational potential energy of an object in a gravitational field, like a planet, is considered negative energy because it takes work to move the object from the source of gravity to a point where this energy would be zero, for example, to infinity. This form of negative energy is the cornerstone of our understanding of gravitational interactions in the universe. However, the negative energy required for the Alcubierre drive is different. In this context, negative energy refers to a hypothetical form of energy whose energy density is less than zero. It's not just an accounting tool or a way of describing potential energy in a gravitational field, but rather a real physical substance or field with exotic properties, such as repulsive gravitational effects. This type of negative energy is not something we observe or well understand in the context of known physics. However, the existence of negative energy and, by extension, exotic matter, remains a topic of intense debate and speculation in physics. Although phenomena such as the Casimir effect suggest the possibility of the existence of negative energy under certain conditions, harnessing it on the scale required for warp drive is a challenge. These challenges, the enormous energy requirements, and the need for exotic matter, underscore the monumental task of transforming Alcubierre drive from a theoretical model to a practical reality. They represent not just technological obstacles, but fundamental questions about the nature of the universe and our ability to manipulate its basic forces. As we move forward into the world of warp drive technology, we face another obstacle known as the horizon issue. This issue is at the heart of the Alcubierre drive design and poses serious problems for its practical application. In astrophysics, the horizon is often referred to as the boundary beyond which events cannot affect an outside observer. The most famous example is the event horizon of a black hole, the point of no return. Beyond this horizon, the gravitational attraction is so strong that nothing, not even light, can leave it. Similarly, in Alcubierre drive, the horizon is the boundary of a warp bubble. Inside this bubble, the spaceship is cut off from the rest of the universe, just as the interior of a black hole is isolated from the outside world by its event horizon. The horizon problem arises from the unique structure of the warp bubble itself. In the Alcubierre model, the spacecraft is located in a region of the space-time plane surrounded by a warp bubble that compresses space at the front and expands it at the back. This manipulation of space-time allows travel at speeds faster than the speed of light, but with a critical limitation. It isolates the spacecraft from the rest of the universe. Imagine being inside this warp bubble, the very mechanism that allows you to travel vast distances in space also prevents you from controlling the ship or interacting with the outside world. Communication signals, navigation commands, and even visual observations are all prevented by the bubble's boundary. Passengers and crew will not be able to control the spacecraft, correct its course, or even stop the journey once it's begun. The implications of the horizon problem are profound. It implies that a spacecraft driven by warp would essentially be traveling on a one-way, uncontrolled journey. This raises practical questions about using such technology for exploration or travel. How do we get to specific destinations? How do we avoid collisions with celestial objects, or adjust our flight path to meet unforeseen circumstances? Moreover, this problem implies the need for a pre-established infrastructure, similar to an interstellar highway, with mechanisms to create and control the warp bubble from the outside. Such a requirement adds another layer of complexity to the already difficult task of realizing warp drive technology. While the horizon problem represents a significant engineering challenge, it is important to recognize that it doesn't invalidate the fundamental scientific validity of the concept. Theoretically, the principles underlying the warp drive remain unchanged and plausible within the framework of the general theory of relativity. As we delve deeper into the complexities of Alcubierre drive, we encounter another major problem, the radiation problem. This problem is twofold. It involves both the accumulation of radiation at the front of the deformation bubble and the potential effects of Hawking radiation within the bubble itself. First, let us consider the radiation accumulating at the front of the warp bubble. As the bubble moves through space at a speed faster than the speed of light, it inevitably encounters interstellar particles and cosmic radiation. These particles and radiation, unable to bypass the warp bubble, accumulate near its front end. Such accumulation poses a significant risk. When the warp bubble slows or stops, the collected radiation and particles will be released in a burst of energy. The intensity of this release could be catastrophic, not only endangering the spacecraft and its passengers, but potentially damaging any nearby objects at the destination. Moving inside the warp bubble, we encounter the second aspect of the radiation problem, Hawking radiation. This theoretical radiation, predicted by Stephen Hawking, arises from the effects of quantum mechanics near the edges of black holes. In the context of Alcubierre drive, the intense warping of space-time around the edge of the bubble could create conditions similar to those at the event horizon of a black hole, potentially generating Hawking radiation. This radiation could have harmful effects on passengers inside the bubble, exposing them to high levels of energy and particles. The implications of these radiation problems are profound. Not only do they pose serious engineering and safety challenges, but they also raise questions about the feasibility of long-duration travel using Alcubierre drive. Ensuring passenger safety and spacecraft integrity in the face of these radiation hazards is a critical area requiring further research and innovative solutions. It is a challenge that requires ingenuity and a deeper understanding of the interplay between quantum mechanics, the theory of relativity, and the harsh reality of space travel. When we turn our eyes to the current state of research in warp drive technology, we find ourselves in the thick of scientific research. Recent years have seen a flurry of theoretical papers and articles that break new ground in this field. One notable development has come from the work of physicists who've been revisiting the energy requirements of the Alcubierre drive. Based on earlier advances that significantly reduce the estimated energy requirements, recent papers have proposed various methods to further optimize the geometry of the warp bubble. These improvements are aimed at making the energy requirements even more feasible, approaching the realm of possibility. Significant contributions to the field have been made by researchers such as Harold White, who was instrumental in the experimental work on the feasibility of deformation bubbles and space-time manipulation at the NASA Eagle Works laboratories. Another area of active research is exploring alternative theories that could circumvent some of the limitations of the Alcubierre drive. For example, some physicists are exploring the possibility of using solitons, solitary waves that retain their shape while traveling at a constant speed, as a basis for creating stable strain bubbles without the need for negative energy. There's also growing interest in the role of quantum mechanics in warp drive physics. Researchers are delving into the quantum aspects of space-time and how they might affect warp drive mechanics. This includes studying the effects of quantum entanglement and the potential use of quantum fields to stabilize the warp bubble. Recent theoretical advances also include the study of the effects of warp drive technology on causality and the fabric of space-time. These studies are critical in addressing potential paradoxes and time travel scenarios, ensuring that the concept remains grounded in physical laws as we know them. Little by little, the dream of warp drive technology is moving ever closer from the pages of science fiction into the realm of scientific possibilities, driven by the tireless efforts of researchers around the world. As we ponder the future of warp drive technology, we find ourselves at a crossroad of assumptions and possibilities. The realization of warp drives, a concept once confined to the realm of science fiction, depends on several key developments and breakthroughs. First of all, the theoretical problems associated with warp drive technology need to be addressed. This includes finding viable solutions to the enormous energy requirements, the creation and stabilization of warp bubbles, and the safe management of radiation risks. Advances in areas such as quantum mechanics, exotic matter, and energy manipulation are critical to turning these theoretical possibilities into practical reality. Beyond the scientific and technical obstacles, the advent of warp drive technology brings with it many ethical and practical considerations. The ability to travel vast distances in space at unprecedented speeds would revolutionize space exploration, opening new horizons for humanity. However, with great power comes great responsibility. The ethical implications of such technology must be carefully considered. This includes the potential impact on space ecosystems, the responsibility to explore and possibly interact with extraterrestrial life, and equal access to this technology among nations and peoples. In practice, warp drive technology could lead to new methods of resource utilization, new ways of conducting scientific research, and even the possibility of interstellar colonization. This would fundamentally change our relationship with space, from one of exploration to one of habitation and utilization. For now, we look forward to a future in which stars are not just points of light in the night sky, but destinations within our reach. This future promises uncharted territories and unprecedented exploration, beckoning us to continue our quest for knowledge and discovery. Supernovae are not just amazing events in the universe. They're vital cosmic phenomena that shape and create galaxies. These powerful explosions occur at the end of a massive star's life cycle, ejecting elements into space from which new stars, planets, and even life itself are formed. In essence, supernovae serve as both destroyers and creators of galaxies. In the study of supernovae, imagery plays a crucial role in understanding these powerful explosions. Over the years, advances in imaging technology have allowed astronomers to capture spectacular views of supernovae at different stages, revealing intricate details of their structure and the elements they eject into space. The story of Betelgeuse, a red supergiant star, is a prime example of how images help us understand the behavior of supernovae. Betelgeuse has recently attracted a lot of attention due to its sudden fades and increases in brightness. This variability has led to speculation of its imminent explosion, sparking widespread interest. The appearance of a dust cloud around the star, observed in telescopes and captured on images, was initially taken as a precursor to a supernova. However, later it began to be considered as a natural phenomena in the life cycle of red supergiants. So why did scientists initially hypothesize the possibility that this star would be the next observed supernova? This red supergiant occupies a prominent place in the constellation of Orion, perched on its shoulder, and is visible to the observer even to the naked eye. Let's take a look at the life cycle of Betelgeuse, an intriguing journey that will show the evolution of the star from its birth to its current state as a massive, pulsating giant nearing the end of its life. Betelgeuse began its existence as a massive star burning hydrogen in its core, like many others. However, because of its large mass, it evolved rapidly, entering successive phases of nuclear fusion. The significant mass of the star distinguished its evolutionary path from the evolution of smaller stars, such as our Sun. While the Sun is currently a stable main-sequence star slowly converting hydrogen into helium, Betelgeuse, due to its much larger mass, more quickly depleted its hydrogen reserves and evolved into a red supergiant. The key difference between Betelgeuse and our Sun is their masses. Betelgeuse, which has about 15 to 20 times the mass of the Sun, experiences higher pressure and temperature in its core, which accelerates nuclear fusion. Intense fusion causes Betelgeuse to burn its fuel rapidly, resulting in an unstable structure and significant brightness fluctuations. In contrast, the Sun's lower mass allows it to remain stable for billions of years, with a much longer and more stable hydrogen burning phase. As Betelgeuse aged, it entered successive phases of nuclear fusion, gradually burning off elements heavier than hydrogen. Internal pressure caused the star to begin to swell, transforming it from a main-sequence star into a red supergiant. This stage is characterized by Betelgeuse's enormous size and variability in brightness. The star expands and contracts as it undergoes complex nuclear processes. Recent observations have suggested that Betelgeuse may be on the verge of a supernova. The star's dimming in 2019, followed by an unexpected increase in brightness, has led scientists to speculate that it may be approaching the final stage of its life. These changes in brightness are thought to be related to internal processes, possibly signaling the beginning of core collapse. The star's pulsations, with cycles of 185, 230, 420, and 2200 days, were analyzed to understand its internal dynamics. The longest cycle of 2200 days is particularly intriguing because it may represent Betelgeuse's fundamental pulsation mode, indicating its advanced stage of evolution. These observations, along with recent telescopic findings, suggest that Betelgeuse may be entering a phase of carbon combustion that precedes a supernova explosion. But what are the complex nuclear processes that dictate when a star's life must come to an end? At the center of a massive star like Betelgeuse, nuclear fusion turns hydrogen into helium, releasing enormous energy. As the star ages, heavier and heavier elements fuse to form bulb-like layers. Eventually, the core is filled with iron, which cannot release energy during the fusion process, leading to gravitational collapse. As the core collapses, a runaway reaction is triggered. In this process, the iron core collapses under enormous gravitational forces, reaching temperatures of billions of degrees. This leads to the rebound effect, where the core inflates and then explodes, creating a shockwave that rips the star apart. A supernova explosion releases an enormous amount of energy, briefly eclipsing an entire galaxy. The mechanics of this process involve a complex interplay between nuclear collapse, gravitational forces, and intense heating. The shockwave generated by the collapse of the core propagates outward, ejecting the outer layers of the star into space. Ancient astronomers have recorded these bright phenomena for thousands of years, sometimes describing them as guest stars. or new stars. The earliest recorded supernova observation dates back to 185 AD when Chinese astronomers observed guest stars, as they called them, that were visible for 8 months. Although rare, astronomers continue to study them to this day, especially when they lead to unusual phenomena such as gamma-ray bursts. Gamma-ray bursts, or GRBs, are intense bursts of gamma rays, usually associated with the collapse of massive stars or the merger of neutron stars. These bursts are some of the most energetic events in the universe, capable of releasing more energy in just a few seconds than the Sun will emit in its entire 10 billion-year lifetime. The discovery of the Boat GRB, also referred to as the brightest of all time, in October 2022, was a milestone in GRB observations, stunning astronomers with its unprecedented brightness and startling impact on Earth. The Boat GRB, officially designated GRB 221009A, was detected on October 9, 2022, and originated from a galaxy about 2.4 billion light-years away from Earth. The event was unusual not only in its brightness, but also in its duration. It lasted about 7 minutes, much longer than a typical gamma-ray burst. The burst was so powerful that it affected the Earth's ionosphere, temporarily disrupting radio communications and altering the ionization of the atmosphere. The relationship between supernovae and gamma-ray bursts is complex and fascinating. In some cases, the collapse of the core of a massive star can trigger a GRB, especially if the star is rapidly rotating and has a strong magnetic field. Such long GRBs often last more than 2 seconds and are often followed by a supernova explosion. Boat was notable not only for its brightness but also for providing insight into the formation of heavy elements. In April of this year, scientists studied this burst in detail, initially hoping that it might provide clues about the origin of elements heavier than iron, which are usually formed in supernova explosions or neutron star mergers. However, further analysis showed that GRBs do not produce these elements, leaving scientists even more puzzled and emphasizing the mysterious nature of such cosmic phenomena. To find out exactly what caused the flare, scientists used a variety of observational tools, including the James Webb Space Telescope. The exceptional brightness of the flare initially obscured its surroundings, making it difficult to observe the accompanying supernova or other objects in the host galaxy. It took several months before the brightness diminished enough to make detailed observations possible. As a result, a relatively undetectable supernova remnant was detected, which was surprising given the power of a gamma-ray burst. The Boat GRB also provided insight into the characteristics of gamma-ray bursts. The exceptional brightness and long duration of this event indicated that the GRB was very focused, with narrow jets pointing directly toward Earth. This narrow directivity likely contributed to the observed intense brightness, as gamma-ray bursts tend to be directional phenomena. The narrow burst jets were probably the result of a rapidly rotating star with a strong magnetic field that produced a powerful and focused flare. While Boat GRB has provided insight into gamma-ray bursts and supernovae, scientists continue to find answers to the mysteries of Betelgeuse. Recent research suggests that Betelgeuse's cycles of dimness and brightness are part of its natural behavior as a variable star. It turns out that, unlike our Sun, Betelgeuse is an extremely explosive and low-density plasma cloud that changes shape frequently. Created by scientists, simulation illustrates the behavior of Betelgeuse in time. Periods of brightness and dimness occur about every 400 days, and the longer cycle is about 2,000 days. Recent studies have tried to explain the Great Dimming phenomena that occurred in 2020, and observations from various telescopes over the past 15 years have provided much insight. observations at various frequencies, including microwaves and infrared, have allowed scientists to penetrate the layers of Betelgeuse and detect silicon monoxide, indicating the presence of a large dust cloud. This discovery disproved initial speculation that Betelgeuse was about to explode. Instead, it appears that internal activity within the star has caused the material to separate, forming a large gas cloud. The formation of a cold region beneath this cloud caused particles to condense, creating a dark cloud that obscured Betelgeuse from view from Earth. Further study of Betelgeuse's behavior revealed that the star experienced two shockwaves, one in 2018 and another 1 year later. These waves disrupted the surface, creating hot and cold spots, which was confirmed by Hubble Space Telescope ultraviolet imaging observations. The shockwaves and their aftermath disproved the initial assumption that Betelgeuse was close to a supernova, and instead showed that this behavior of the star is part of its natural life cycle. Betelgeuse's behavior is also characterized by its high rotation rate. Unlike typical red supergiants, which rotate slowly, Betelgeuse rotates at about 3 miles per second, which initially led researchers to think that it might have been a binary star that collided. However, recent research suggests that this rotational speed may be influenced by fast-moving convective cells inside the star, contradicting initial assumptions about its rotational behavior. Despite the unusual behavior, this research suggests that Betelgeuse is unlikely to become a supernova in our lifetime. The current state of the star is more like a variable red supergiant nearing the end of its life, but by no means approaching a supernova explosion. So finally we come to the very question that concerns all of us. How would such an explosion affect our home planet? The potential impact of a nearby supernova on Earth is a subject of speculation and concern. While a supernova is not expected to pose an immediate threat to our home, the explosion of a star within a few light years could affect Earth's atmosphere and potentially impact life. For example, the flare of the very same boat GRB was so intense that it significantly affected the Earth's ionosphere, altering atmospheric conditions and disrupting radio communications. The flash released a tremendous amount of energy that interacted with the Earth's atmosphere, causing a sudden increase in ionization. This increased ionization affected the ozone layer and triggered chemical reactions that scientists are still trying to understand. The GRB also disrupted radio signals, especially those used for communication and navigation. The energy released in the explosion was so great that it even blinded several satellites, demonstrating the enormous power of these cosmic phenomena. However, the burst itself was observed from a galaxy a whopping 2.4 billion light-years away. This event only emphasizes the need for further study of gamma-ray bursts to understand their impact on us, our planet, and the universe as a whole. In addition, supernova studies also contribute to our understanding of dark matter, dark energy, and the overall structure of the universe. Type 1a supernovae, which occur in binary star systems, are crucial for measuring cosmic distances and studying the expansion of the universe. These standard candles have helped astronomers detect the accelerating expansion of the universe, which in turn has provided the background for understanding dark energy. Supernovae are a key focus of future astronomy. Their explosive nature and transformative impact continues to fascinate scientists and inspire discovery. Well, while some people are frozen in anticipation of the Betelgeuse explosion on live internet feeds, we look forward to discoveries from missions such as the Vera Rubin Observatory and the European Space Agency's Euclid Telescope, which will contribute to advancing our understanding of supernovae. As we look deeper into space, these stellar explosions will undoubtedly shape our understanding of the universe and our place in it. Humanity stands on the threshold of a new era, an era defined not only by exploration, but also by the bold dream of colonization. For decades, our gaze has been fixed on the familiar, the Moon, our celestial neighbor, and Mars, the red beacon in our night sky. These worlds, once the subject of science fiction, now beckon us with the promise of new frontiers. But beyond these well-trodden paths lies a world shrouded in mystery, a world that's changing our understanding of what it means to be a moon. This is Titan, Saturn's largest satellite. Titan is a world covered with a dense atmosphere, which is rare for a moon. It's a place where rivers and lakes flow not with water, but with liquid methane and ethane. Here, the sky is raining gasoline, and the cold is beyond anything that can be experienced on Earth. Yet, in this alien landscape lurks the potential for something extraordinary. Could Titan, a world so unlike our own, hold the key to our future in space? Could this distant moon hold the secrets to not only surviving, but thriving beyond our home planet?
It's one small step for man, one giant leap for mankind.
As we turn the pages of our history of space exploration, the Moon and Mars become beacons of human ambition. The Moon, our nearest celestial neighbor, has always been a constant companion in our night sky, a symbol of our desire to leave the confines of the planet. Mars, in turn, with its striking resemblance to Earth, fuels our dreams of finding a new home in space. Nevertheless, the Moon, despite its proximity, presents serious problems. Its surface is a barren wasteland, devoid of atmosphere and offering no protection from the harshness of space. The lunar environment is a vacuum, exposing astronauts to extreme temperatures and cosmic radiation. No atmosphere means no air to breathe, no wind to carry sound, and no sky to protect against the relentless barrage of solar and cosmic rays. Mars, though more Earth-like, is not without its own problems. Its thin atmosphere, consisting mostly of carbon dioxide, offers little protection from solar and cosmic radiation. The Martian environment is harsh and merciless, and temperatures at the poles can drop to minus 257 degrees Fahrenheit. The lack of a global magnetic field exposes the surface to the full force of the solar wind and cosmic rays. In contrast, Titan, Saturn's largest satellite, presents a very different environment. Shrouded in a dense atmosphere, Titan offers a natural barrier against the dangers of cosmic radiation. This atmosphere, richer in nitrogen than even the Earth's atmosphere, is the key to protecting future colonists from cosmic rays that mercilessly bombard less protected worlds such as the Moon and Mars. Titan's atmosphere isn't just a shield, it's a gateway to opportunity. Unlike the Moon and Mars, the air pressure on Titan's surface is 1.5 times higher than on Earth, creating a surprisingly familiar pressure environment for human explorers. This dense atmosphere opens up new possibilities for exploration and colonization, possibilities that are beyond the reach of our more trivial space goals. As we rethink our goals for space colonization, Titan becomes a compelling alternative, a world in which the atmospheric and radiation problems that limit our ambitions on the Moon and Mars become its strengths. Titan invites us to envision a future in which humanity can thrive under the protective embrace of an alien sky, a future in which the mysteries of this distant moon become stepping stones to our expansion into space. As we mentioned earlier, Titan, a moon of many mysteries, orbits around Saturn. Discovered in 1655 by Dutch astronomer Christian Huygens, Titan has captivated the imagination of scientists and dreamers ever since. This world is both similar to and in stark contrast to our Earth. Titan's environment is unlike anything else we've encountered in our solar system. It's the only known moon with a dense atmosphere, and the second largest moon in our solar system after Ganymede, a satellite of Jupiter. But it's not just the size that makes Titan stand out, it's the rich composition of its atmosphere and surface that really sets it apart. This moon is surrounded by a thick, nitrogen-rich atmosphere, similar in composition to Earth's, but far denser and more extensive. It's permeated with organic molecules, creating a kind of hazy orange glow that obscures the surface of the satellite from view. It's this nitrogen-dominated atmosphere that provides protection from solar radiation, which contrasts sharply with the barren sky of the Moon and Mars. Beneath this alien sky lies a landscape at once familiar and utterly alien. Titan's surface is formed by rivers and lakes, but they're not bodies of water as we know them. Instead, they're filled with liquid methane and ethane, flowing through channels carved into the Moon's icy crust. These hydrocarbon seas are a true marvel, a testament to the diversity of the universe's chemistry. The presence of these surface fluids is a key characteristic that distinguishes Titan from other celestial bodies. On Earth, the water cycle shapes climate and geography. On Titan, a similar cycle occurs, but the role of water is played by methane and ethane. This hydrocarbon cycle, with methane rain and ethane lakes, creates a dynamic environment that may provide clues to understanding the complexity of planetary atmospheres. So, by breaking the limits of our standard perception, we're slowly uncovering exactly what makes a planet or moon habitable. Its nitrogen-rich atmosphere and surface fluids open the door to new possibilities. Let's find out what they are. So the Moon's nitrogen-rich atmosphere provides a natural barrier against cosmic radiation, a major challenge for space colonization. Why do we pay so much attention to solar radiation? Well, the answer is simple, yet profoundly important. Solar radiation is a ruthless destroyer of living cells. It doesn't just affect microscopic life forms, it directly affects us as human beings. Unshielded exposure to solar radiation can cause severe cellular damage, destroying the very fabric of our biological existence. In space, spreading uncontrollably, this radiation poses one of the greatest threats to the survival and health of astronauts. On Earth, it's the atmosphere and magnetic field that protect us. On Titan, it's the dense nitrogen atmosphere that provides vital protection, making it a safer haven for future human colonists than the barren landscapes of the Moon or Mars. Beneath this protective dome is a world of liquid methane and ethane. These hydrocarbon lakes and rivers stand in stark contrast to the bodies of water we know on Earth, yet they offer intriguing possibilities. Imagine a world where boats sail on methane seas, where the familiar concept of the liquid cycle takes on a whole new form. The presence of these surface fluids is not just a curiosity, it's a resource. Methane and ethane have the potential to be used as fuel, providing energy for future colonies. This abundance of hydrocarbons makes Titan an attractive target for colonization, offering a solution to one of the biggest problems of space habitation: sustainable energy sources. But Titan's gifts don't end there. Beneath its icy surface lies another treasure: water ice. The very water so essential to human life is abundant on the satellite, trapped in its frozen crust. The presence of water ice, along with hydrocarbons, makes this moon a repository of vital resources, setting the stage for a self-sustaining human presence away from Earth. Titan, a world of incalculable potential, also presents enormous challenges. Severe cold, during which temperatures drop to minus 356 degrees Fahrenheit, creates an environment unsuitable for human life as we know it. In turn, methane rain, a phenomenon unique to this moon, adds another layer of complexity to the survival equation. To overcome these challenges, we must turn to the pinnacle of human ingenuity and technology. Colonizing Titan will require not just adaptation, but a complete rethinking of human habitation in extreme conditions. Imagine dwellings designed to withstand low temperatures, insulated with materials yet to be invented, and harnessing the power of Titan's own resources to provide warmth and comfort. These habitats could be equipped with systems to convert atmospheric methane into heat, turning the problem itself into a resource for solving it. But survival is more than just keeping warm. Methane rain, while an obstacle, could turn into an advantage. Advanced collection and filtration systems could recycle methane not only as an energy source, but also as a raw material for essential commodities. Now, let's imagine a human colony on Titan. Imagine domed cities, their architecture a blend of science and art, designed to harmonize with Titan's unique environment. These structures, resistant to cold and methane rains, would be interconnected, forming a network, demonstrating human resilience in the face of alien conditions. Inside these domes, life thrives. Hydroponic gardens provide food, recycling systems conserve resources, and public areas foster a sense of community. It's a place where humanity has not just survived, but flourished, adapting decisively to Titan's challenges. Colonizing Titan is not just a distant dream, it's a future that beckons us to take up the challenge. With each technological breakthrough, with each bold leap of imagination, we come closer to making this alien world a new home for humanity. Watching the thriving human colony on Titan, it becomes clear that this moon is more than just a new home for humanity. It's a center of economic and scientific opportunity. The unique environment and abundant resources offer unprecedented prospects for both. The economic benefits of colonizing Titan are rooted in its vast hydrocarbon reserves. Key components of Titan's lakes and atmosphere are not only potential sources of energy, but also valuable raw materials for chemical synthesis. The ability to harness these resources could turn Titan into an economic center, meeting both the colony's needs and potentially supplying materials for interplanetary trade. Scientifically, Titan is a gold mine. Its complex atmosphere and surface chemistry offer unique research opportunities that offer insights into organic chemistry and astrobiology. Studying Titan's methane cycle and its prebiotic chemistry could unlock the secrets of the origin of life, not only on Earth, but potentially throughout the cosmos. Moreover, Titan's position in the solar system and its resources make it an ideal launching pad for future space exploration. Its low gravity and abundant fuel reserves could make it easier to launch spacecraft to distant destinations, making Titan a strategic outpost for exploring the outer solar system and beyond. However, with these opportunities come important ethical considerations. As we embark on the colonization of Titan, we must reflect on our responsibilities in interacting with the new world. Conservation of Titan's environment, respect for its unique characteristics, and thoughtful stewardship are paramount. We must approach Titan not as conquerors, but as custodians. How we relate to this world in the future will reflect our values and our ability to balance progress and responsibility. As we conclude our journey, let's reflect on the key points. A moon once shrouded in mystery has turned out to be a world full of potential. We explored the protective properties of Titan's nitrogen-rich atmosphere, a natural shield against the dangers of cosmic radiation. We traveled through alien landscapes where rivers and lakes of methane and ethane cut through icy terrain, offering resources that could secure our future in space. Our journey also took us to the potential of a vibrant human habitat, where ingenuity and resilience have turned challenges into opportunities. We saw how Titan's economy, driven by its abundant resources, can be a cornerstone of our interplanetary endeavors. As we ponder the future of humanity on Titan, we're reminded that colonization is not just about achieving technological perfection. It's a journey that forces us to grow, learn, and respect the universe we live in. So we leave you with a great question. What does this step mean for the future of humanity? How will our efforts on this distant moon affect our destiny in the vast, uncharted expanse of space? In the vast theater of our solar system were planets like Jupiter and Saturn, often attract attention with their majestic rings and violent storms, lies a distant world shrouded in mystery and intrigue. This is Uranus, an enigmatic ice giant that often goes unnoticed, but holds secrets that may unravel some of the most enduring mysteries of the cosmos. Far beyond the asteroid belt, nestled between the orbits of Saturn and Neptune, Uranus travels through the cold and dark corners of our solar system. It's a world that lives at a different rhythm, spinning on its side, an oddity that's long puzzled astronomers and spawned countless theories. Discovered in 1781 by William Herschel, Uranus was the first planet discovered through a telescope, extending the known boundaries of our solar system. For centuries, this distant world was just a speck of light in our telescopes, a ghostly blue ball, distant and aloof, keeping its secrets. But now, with the advent of the James Webb Space Telescope, a new chapter in the exploration of Uranus is opening. JWST, with its unprecedented vision, peels back the layers of this icy giant, revealing a world of amazing beauty and complexity. Let's travel together to this mysterious ice giant and learn about the latest discoveries made by the James Webb Space Telescope. In the quest to understand the universe, humankind has launched a sentinel into space, a marvel of engineering and a testament to our insatiable curiosity. This sentinel is the James Webb Space Telescope, the most advanced and powerful space telescope ever built, the successor to the legendary Hubble Space Telescope. Equipped with a set of advanced instruments and a mirror more than 6.5 meters in diameter, JWST is designed to observe the universe in light invisible to the human eye, the infrared spectrum. This allows the telescope to peer through clouds of cosmic dust, discover distant galaxies, and study the atmospheres of exoplanets. The telescope's journey into space was a feat in itself. Launched on an Ariane 5 rocket, JWST traveled to a point in space known as the Second Lagrange Point, or L2, 1,000,000 miles from Earth. Here, in this stable orbit, JWST can observe the universe with minimal interference from Earth and the Sun. JWST's capabilities are not limited to observing the early universe or distant galaxies. It plays a key role in unlocking the mysteries of our solar system. Its powerful instruments, such as the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, reveal new details about planets, moons, and other celestial bodies closer to home. Take Uranus, for example. In the past, our view of this distant planet was limited to faint images from telescopes such as Hubble. But now, thanks to JWST's enhanced infrared capabilities, we can see Uranus in a new light. The telescope's sensitive instruments allow us to observe the planet's atmosphere, weather patterns, and even its mysterious rings with unprecedented clarity. By analyzing the light of Uranus, JWST can decipher the chemical composition of its atmosphere, revealing the presence of gases such as methane and hydrogen. This not only helps us understand the current state of Uranus, but also provides clues about its formation and evolution. The James Webb Space Telescope continues to exceed expectations, revealing more details about our universe every day. Its latest triumph is a series of images of Uranus taken very recently, surpassing even the stunning observations made in April 2023. In early 2023, JWST provided us with unprecedented views of Uranus, allowing us to look at the planet's atmospheric dynamics and ring system in a new light. The recent images, however, are a step further. Not only are they clear, they reveal aspects of Uranus that were previously hidden or obscured, even in April observations. Take the rings of Uranus, for example. The latest images show them with even greater clarity. We can now observe finer structures within the rings and even detect faint dust bands that were previously invisible, such as the Zeta ring, the incredibly thin ring closest to the planet. The strength of JWST lies not only in its one-off observations, but also in its ability to continuously track celestial objects. Continuous observations of Uranus have allowed us to observe changes in the planet's atmosphere, track the movement of its clouds, and observe the evolution of its storms over time. The changes in the polar regions are particularly striking. Bright white caps and dark bands near the poles, the origin of which is still unclear, have shown marked changes. This continuous observation provides invaluable data for understanding the seasonal changes and long-term climate patterns of Uranus. In the set of planets in our solar system, Uranus stands out with a peculiar feature, an extraordinary axial tilt. Unlike any other planet, Uranus rotates practically on its side, tilted at an angle of about 98 degrees. This unique orientation has long intrigued astronomers and sparked a quest to understand its origin and consequences. To understand the significance of this tilt, we must travel back in time to the early days of our solar system. Uranus probably formed with a much less severe tilt. The prevailing theory suggests that a catastrophic event, perhaps a collision with a planet-sized object, dramatically changed its orientation. This colossal impact would have thrown Uranus aside, changing the definition of its axis of rotation. Such a dramatic event in the planet's history probably not only changed its rotation, but also left an indelible mark on its entire system, including its satellites and rings. Today, this lateral rotation is a unique spectacle. Each pole of Uranus is alternately flooded with sunlight and plunged into darkness at intervals of 42 years. This extreme tilt results in extreme seasons, unlike those observed on other planets. The implications for planetary observations and research are enormous. Uranus's tilt allows us to observe its rings and satellites from different perspectives, offering insights into their composition and dynamics. For example, when Uranus's rings face the Earth, they become nearly invisible, exposing fainter dust bands and smaller satellites. Compare that to Earth, which is tilted only 23.5 degrees. Uranus's extreme tilt causes drastic changes in its weather patterns, which is a goldmine for scientists studying planetary climate. Tilt also affects the circulation of Uranus's atmosphere. Prolonged exposure to sunlight at the poles can result in complex weather systems, as seen in recent JWST images. These systems are very different from those on other planets and provide a unique laboratory for understanding atmospheric physics. Let's take a journey on one Uranian year. Each season on Uranus lasts about 21 Earth years, a consequence of its 84-year orbit around the Sun. This extended duration means that each hemisphere experiences long periods of daylight, followed by equally long nights. As a result, the planet undergoes dramatic changes in appearance and climate. Because one pole of Uranus basks in uninterrupted sunlight, summers are long, while the opposite pole plunges into a deep, dark winter. This stark contrast creates unique atmospheric conditions, causing complex weather patterns and climatic shifts. The impact of these seasonal changes on Uranus's atmosphere is profound. When the sun illuminates the planet's surface, it warms the atmosphere, creating colossal storms and dynamic cloud systems. These atmospheric phenomena are not static. They evolve and change with the seasons, painting an ever-changing portrait of the planet. Among the most striking features are the bright cloud tops that appear when the sun illuminates the planet's atmosphere. These clouds, composed of frozen methane and other gases, reflect sunlight, creating a dazzling spectacle. Conversely, dark storm patches that look like giant hurricanes roam the planet's surface. Moreover, the planet's seasonal phenomena affect not only the planet itself, but also its moons. One recent study of Uranus's moons, or rather a phenomenon that's particularly intriguing, is the development of temporary atmospheres on these moons. a spectacle caused by the unique conditions of the Uranus system. The key to understanding these temporary atmospheres lies in the extreme tilt of Uranus's axis and its effect on the satellite's orbits. As these satellites orbit the planet, they experience dramatic changes in solar exposure, alternating between long periods of intense sunlight and prolonged darkness. During the long summer exposed to sunlight, the icy surfaces of these satellites undergo a process known as sublimation. The ice, composed mainly of water, methane, and carbon dioxide, transforms directly from solid to a gas, bypassing the liquid phase. This sublimation creates thin, temporary atmospheres, or exospheres, that envelop the satellites. These exospheres are most pronounced when moons are warmest. Recent research by the James Webb Space Telescope shows that this phenomena is more dynamic and complex than previously thought. Exospheres are heterogeneous. They vary in composition and density, depending on the topography of the moons and the intensity of solar radiation. As the satellites enter their winter phase, the exospheres gradually dissipate. Gases recondense on the surface, returning to an icy state. This cycle of atmosphere creation and disappearance is a unique characteristic of Uranus's satellites, opening a window into the interaction between solar radiation and surface ice. The rings of Uranus, often overshadowed by the majestic rings of Saturn, hold their own tale of cosmic intrigue and dynamism. A recent comparative study of the rings of Uranus, Saturn, and Jupiter sheds new light on these lesser-known, but no less fascinating, celestial features. In contrast to the wide and bright rings of Saturn, the rings of Uranus are narrow, dim, and less extensive, extending to 4 planetary radii. This includes elusive rings, such as the Mu and Nu rings. The study delves into the gravitational influence of Uranus's main satellites on these rings, a key factor in their formation and evolution. The significant influence of Uranus's 5 major satellites, Miranda, Ariel, Umbriel, Titania, and Oberon, plays a central role in the history of the rings. These satellites, much more massive than their smaller counterparts, dominate the gravitational dynamics within the Uranus system. Their positions and masses relative to Uranus provide a better understanding of the formation of the satellites and the gravitational formation of the rings. The formation of Uranus's rings is attributed to a combination of processes, including collisions, satellite breakup, and gas release from the main satellites. These dynamical processes affect the material composition of the rings and are influenced by the ever-changing environment of the Uranus system. The stability of the rings is intrinsically linked to their dynamical interactions with the satellites of Uranus. The study examines how accretionary processes occur within the Roche limit and how the dynamics of shepherding moons play a crucial role in maintaining the rings. In addition, the rings provide a unique opportunity to understand the internal structure of Uranus through seismological studies. Modeling results show how these satellites shape the ring system, affecting its structure and stability over time. The modeling predicts significant material loss within the ring system, primarily due to gravitational interaction with the satellites. The complex dance between moons and rings is a key aspect of the Uranus system. The dynamic exclusion zones created by the satellites and the influence of these zones on the material distribution of the rings are crucial to understanding the structure and the evolution of the rings. The study also examines the role of satellite-to-satellite interactions in the evolution of the system, especially past resonances between satellites such as Ariel and Umbriel, and their impact on the orbits and geology of satellites, especially Miranda. But the mysteries surrounding this planet don't end there. You've probably heard of the aurora borealis. Well, the latest discovery concerns the auroras of Uranus, which also has them. However, its auroras, unlike Earth's, occur in the infrared spectrum. Using the Keck 2 telescope, astronomers observed enhanced emissions of trihydrogen cation in the planet's atmosphere. This is a groundbreaking discovery that sheds light on the unique magnetic field and dynamics of Uranus's atmosphere. Uranus's magnetic field, which is significantly deflected from the planet's axis of rotation, creates a unique coupling of the magnetosphere, ionosphere, and thermosphere. The detection of these infrared auroras is crucial because it opens up a new window into these processes, previously elusive due to the lack of such detections on Uranus. Comparing the polar auroras of Uranus with those of Jupiter and Saturn reveals their different characteristics. Unlike Jupiter, where the H3+ emissions have short lifetimes that smooth out the variability of the UV emission, the brightest infrared emissions of Uranus do not necessarily coincide with the brightest UV emissions of the other planets. This unique aspect of Uranus's polar lights provides valuable information for exoplanet studies, especially for the worlds of warm ice giants. The study delves deeper into the unusual heat spots on Uranus, observed near the latitudes of the UV northern lights. These spots, analyzed for temperature, column density, and total emission, suggest that the enhancement is not caused by temperature, but rather by increased ionization, probably due to polar aurora activity. Polar lights play a significant role in heating the atmosphere, and on Uranus, the increased H3+ emissions associated with these auroras suggest their involvement in atmospheric processes. By studying such unique things, we gain a deeper understanding of similar processes in different planetary environments, enriching our knowledge of how auroras shape planetary atmospheres, affecting not only thermal properties, but also the overall dynamics of the ionosphere and magnetosphere. In the quest to unravel the mysteries of our solar system, the ice giants Uranus and Neptune are distant enigmas beckoning closer exploration. Recent research, including a fresh analysis of Voyager images, has revealed that the two planets actually have similar shades of greenish-blue color, fundamentally changing our long-held beliefs. Uranus and Neptune share many common characteristics. They're roughly the same size, have the same mass, and are surrounded by deep atmospheres of comparable materials. Nevertheless, it was long thought that their appearance was quite different. This misconception has now been corrected. Both planets are shown in their true colors, largely influenced by the methane layer in their atmospheres. The need for a dedicated mission to Uranus has never been greater. Such a mission would not only deepen our understanding of the planet itself, but also provide a comparative view of Neptune and other similar icy giants. The mission's potential goals range from studying the unique magnetic field and complex ring system to investigating atmospheric dynamics and internal structure. In an important achievement for planetary exploration, the Uranus Orbiter and Probe mission has been elevated to the highest priority for NASA flagship mission within the 2023-2032 Planetary Science Decadal Survey. Future launch windows are available between 2030 and 2034. Key science goals will include a detailed analysis of the unusual tilt of Uranus's axis and its effect on the planet's climate and weather patterns. The mission can also study the intriguing phenomena of infrared auroras and their role in heating the atmosphere, providing a comparative study with other planets. Studying Uranus and Neptune will also provide valuable information about planetary evolution and dynamics. Understanding why Uranus appears slightly whiter, perhaps due to its more stagnant atmosphere, allowing methane haze to accumulate, can tell us a lot about atmospheric processes on the ice giants. As we await a future mission to Uranus, we stand on the threshold of discoveries that could redefine our understanding of the outer solar system. Exploring this distant ice giant will not only unravel its mysteries, but will also expand our knowledge of planetology as a whole, shedding light on the complex picture of our cosmic home. Our universe hides a mystery that's long captivated the human mind. A question that bridges the gap between the known and the unknown, the simple and the complex. Here on Earth, life thrives in a continuous movement of order and chaos. Every form of life is evidence of a hidden order, a pattern woven into the very fabric of existence, from the smallest microorganisms to the largest mammals. But what if the complexity of life, the very essence of our existence, could be explained not only through the lens of biology, but also through a mathematical framework? This is the territory of assembly theory, a groundbreaking concept that transcends traditional science. It's a journey into a world where math and biology converge to reveal the hidden architecture of life. Imagine a universe in which the secrets of life, from the simplest molecule to the most complex organism, are encoded in mathematical language and are waiting to be decoded, where the line between living and non-living is blurred, giving birth to new possibilities and new understanding. Let's explore how this revolutionary idea is changing our perception of life, evolution, and the cosmos itself. And maybe we can even get closer to answering the ultimate question: what is the true nature of life in the universe? Since the dawn of civilization, mathematics has been the language of the universe, a tool for deciphering the mysteries of nature. But how does this language of numbers and equations relate to understanding the very essence of life? At its core, assembly theory offers a simple but profound idea. The complexity of life can be measured and understood through a mathematical prism. Think of life as a jigsaw puzzle, where each piece represents a molecular building block. Assembly theory seeks to show how these pieces come together step by step to form the complex structures that define living organisms. Each step in this assembly process represents a leap of complexity, from simple atoms to complex proteins. The theory introduces the concept of the assembly index. The assembly index, the cornerstone of this theory, measures the number of steps required to build a biological structure. It's a numerical value that captures the essence of complexity by quantifying the immeasurable. But how does the standard model of physics fit into this? This standard model theory of physics describes the fundamental particles and forces that govern our universe. It seems completely separate from the complexities of biology. However, assembly theory bridges this gap. In the field of assembly theory, the standard model lays the foundation for understanding forces and interactions. It's a bridge between the microscopic world of quarks and leptons and the macroscopic world of living things. Another important element of the theory is the concept of studying dynamical systems, phase space. This is a mathematical concept used to describe all possible states of a system. In the context of assembly theory, phase space allows us to map the path of the assembly of life. From a single point representing the simplest form of life, phase space expands, branching out into almost infinite possibilities. Each pathway representing a different route that life can take. In this limitless mathematical landscape, the paths of evolution and its complexities unfold. This mathematical framework gives us a new perspective on the complexity of life. It's not just about the particles and forces described by the standard model, but how these elements combine and interact over time to create the diverse pattern of life we see around us. This is where the chaos of random molecular interactions gives way to the order of living structures. So let's ask ourselves this question: are the complexities of life simply the product of chance, or is there a deeper cause? Let us consider two sharply contrasting concepts: complexity and entropy. Entropy, a measure of disorder and randomness, seems to be at odds with the complexity we observe in life. How do these opposing forces coexist in the natural world? It's here that assembly theory offers a revolutionary perspective. So, central to assembly theory is the assembly index, a revolutionary tool designed to measure the complexity of life. Think of it as a cosmic ruler, measuring the steps required to assemble a biological structure from its simplest components. Imagine a single molecule as the starting point on this scale. As you move up the scale, each step represents a more complex assembly, from molecules to cells and beyond. The higher the index, the greater the complexity, and the less likely it is that the structure could have arisen by chance. Now let's delve into the interaction between entropy and complexity. Entropy, a concept rooted in thermodynamics, suggests that systems naturally tend toward disorder. However, life defies this tendency, evolving from simple origins to a variety of forms combined into the complex ordered structures we see today. How does assembly theory resolve this apparent contradiction? It suggests that life is inherently a process of overcoming entropy. Through the lens of the assembly index, we see the complexity of life is not a challenge to entropy, but a journey through it. Consider the early Earth, a primordial soup of simple molecules. Over millennia, driven by the laws of physics and chemistry, these molecules began to assemble into more complex structures. Each step along the way marked a victory over entropy, a step toward greater complexity in life. Rethinking evolution through assembly theory, we see it not as a mere biological process, but as a mathematical inevitability. The emergence and evolution of life became a story of increasing complexity, a story written in the language of mathematics. Let us now turn to a very trivial question, but one that shines in a new light. Are we alone? The search for extraterrestrial life has captivated our imagination for centuries. Now, thanks to assembly theory, we have a new tool in this cosmic quest. Assembly theory offers a unique approach to detecting alien life. It's not about scanning the sky for radio signals or analyzing light spectra for the presence of oxygen. Instead, it's about understanding the complexity of molecules and structures that may indicate life. Imagine scanning the atmosphere of a distant exoplanet or the surface of a moon in our solar system. Using assembly theory, we could analyze the molecular complexity of the samples in search of patterns that indicate the presence of life. The higher assembly index, the more likely it is that these molecules are the result of life rather than random processes. However, the road to discovering alien life is full of challenges and limitations. One of the biggest obstacles is our understanding of life itself. Our definition of life is based on what we know. Life on Earth. What if it doesn't meet our biochemical standards? Another problem is the vastness of space. The universe is vast, and our ability to explore it is limited by current technology. Even with the most sophisticated telescopes and probes, we can only analyze a tiny fraction of the cosmos. Moreover, assembly theory, while powerful, is still in its infancy. It's a new approach, and its application to the search for extraterrestrial life is uncharted territory. There are questions about its applicability and accuracy in different environments, especially those that are very different from terrestrial environments. Despite these problems, the potential of assembly theory in the search for alien life is enormous. It could redefine our understanding of life in the universe, opening new doors in astrobiology. So assembly theory offers a new way of looking at life, not just as a biological phenomenon, but as an emergent property of cosmic complexity. Imagine the early days of our planet, a world in motion, a crucible for the chemistry of life. Here in this chaotic environment, simple molecules began the journey of assembly, a process governed by the laws of physics and chemistry, but leading to something much deeper. Life, according to assembly theory, emerges when these molecular structures reach a level of complexity that allows them to store and reproduce information. This is where chemical memory, a crucial step in the evolution of life, comes into play. Chemical memory is the ability of certain molecular structures to retain structure. In other words, we can say this is the blueprint for life. In the world of assembly theory, this is where reproducibility becomes key. The ability to reproduce these patterns, to pass them on from generation to generation, is what drives the evolution of life. From the simplest RNA molecules in the primordial soup to the vast diversity of life we see today, each step in this evolutionary journey has been a step up the assembly index. Each increase in complexity represents a triumph over the entropy that governs the universe. But the story of the origin and evolution of life is not just a story of increasing complexity. It's also a story of resilience and adaptability. Life has found a way to thrive in the most extreme environments, from the depths of the ocean to the fringes of space. In the realm of scientific discovery, every new theory is scrutinized and debated. Assembly theory, a concept that promises to revolutionize our understanding of life and complexity, now stands at a crossroads, being questioned by critical voices such as Dr. Hector Zennel. The critique presented by Zennel raises fundamental questions about the future evolution of assembly theory. Covering an impressive 18,000 words, the article will require time and thought, taking approximately 1 to 2 hours of dedicated reading. This is not a cursory look at the topic, but a deep dive into the heart of the scientific debate. For those who are interested, we leave a link in the description to both articles, the study and the counter-arguments to it. Looking to the future, the role of assembly theory in scientific research remains uncertain. Will it be able to adapt and overcome these challenges, or will it remain a footnote in the history of science? Despite the disagreements, one thing is clear: the debates surrounding assembly have initiated a conversation about the nature of scientific discovery. They emphasize the need for transparency, rigor, and humility in pursuing knowledge. In the end, the impact of assembly theory on future research may not lie in its specific claims, but in the lessons it teaches us about the scientific process. As we explore the mysteries of life in the universe, such theories will come and go. But the quest for understanding, the quest to unlock the mysteries of our existence, will always remain at the center of the interest of scientific research. Imagine a single point, just a speck of light, hovering in an endless sea of darkness. It's not just a random dot, it's our home, Earth. But what if we told you that this dot is just a fleeting moment in a cosmic panorama so vast and complex that it defies human comprehension? Imagine a night sky decorated with stars, each representing a sun, many of which have their own planets. Now, multiply that image by 100 billion. Even in this case, you've barely touched the surface. Beyond our Earth, beyond our Sun, even beyond our galaxy, lies a structure so vast that everything you know seems like a single thread in an unfathomable cosmic web. The human mind, which is itself a marvel, struggles to grasp this scale. Our brains are built to comprehend the rises and slopes of mountains and the vastness of oceans. But how do we comprehend a structure that stretches billions of light years? Today, we're on a journey to explore these galactic threads, the sinews and muscles of the universe itself. We will venture into a realm of the almost incomprehensible, where even the speed of light seems pedestrian. Spiders weave intricate webs, thin but strong, each thread connected to the other in a complex pattern. Architects of nature create these webs to survive, capture prey, and probe the environment. Now, imagine a web woven not by spiders, but by the very fabric of space and time itself. A web that links galaxies, star clusters, and dark matter into a complex web. This is the cosmic web, the grand architecture of our universe. Each node you see here is not a single star or planet, but an entire galaxy, a colossal cluster of billions of stars, planets, and other celestial objects bound by gravity. But what gives this network this structure? The answer lies in something we can't even see: dark matter. Dark matter, which scientists believe makes up about 27% of the universe, acts as the framework on which this web is built. Although invisible, its presence is felt through the gravitational pull that determines the formation of galaxies and the paths they take. The cosmic web was not always as we see it today. It evolved over billions of years, beginning with tiny fluctuations in the density of the early universe. These fluctuations grew, pulled together by gravity, eventually forming the majestic filaments and nodes we now see. One of the most impressive examples of a galactic filament is the Great Wall of Hercules' northern corona. This colossal structure spans a distance of up to 23 billion light-years, making it one of the largest known structures in the universe. Understanding this network is not just an academic exercise. It's a quest to understand our place in the universe. Are we simply an accidental byproduct of cosmic evolution? Or is there a grander design at work here? Scientists use a range of tools to study this network, from telescopes that can see distant galaxies to simulations that model the behavior of dark matter. Each discovery is a piece of a puzzle, a thread of a story that spans the entire universe. Here it is, Earth, a pearl of blue and green, suspended in the vastness of space. A planet teeming with life, from microscopic to magnificent. It's easy to think of the Earth as the center of everything, but in the grand scheme of the universe, it's just a speck. In our solar system alone, Earth is only one of 8 planets orbiting the Sun, and yet it stands out for its unique ability to support life. The oceans, the atmosphere, the magnetic field. All these elements are in delicate balance. Zoom out even further, and our entire solar system becomes a tiny dot in one of the spiral arms of the Milky Way galaxy, a galaxy that's home to hundreds of billions of stars, each potentially containing its own system of planets. In the Milky Way, it's just one galaxy in a cosmic web of hundreds of billions of galaxies. Each of these galaxies is a node, a focal point in this unimaginable structure. Even within our galaxy, the Earth is influenced by forces beyond its control. Dark matter, the invisible backbone of the cosmic web, shapes the structure of the galaxy and, as a result, the environment around the Earth. Yet despite its seemingly insignificant place in the cosmos, Earth is unusual for one reason: it has life. It's the only known celestial body where life not only originated, but has evolved to an incredible level of diversity and complexity. Humanity's quest to understand its place in the universe has led to remarkable scientific advances. Telescopes peer into remote corners of the universe, and supercomputers simulate the cosmic web, helping to answer fundamental questions about the nature of reality. For example, look at the Sun. The blazing ball of plasma that lights up our sky and warms our planet. It's the reason you can see these very images, the reason life exists on Earth. But in the context of the cosmic web, the Sun is just one node, a lone star among countless others. Close to the Sun, we find other stars, some smaller and cooler, others larger and hotter. Each of these stars is like a bead on a huge cosmic thread, linked together by gravity and dark matter. Our Sun is located in the Orion sleeve of the Milky Way, a small spiral arm located about 27,000 light-years from the center of the galaxy. Even within our galaxy, it is far from special, just one of about 400 billion stars. In the great expanse of the cosmic web, stars like our Sun form complex nodes that connect larger structures, such as galaxies and galaxy clusters. They are the building blocks, the fundamental units that give the web its shape. So what powers this celestial beacon? The answer is nuclear fusion. Deep in the sun's core, hydrogen atoms collide and fuse to form helium, releasing massive amounts of energy. This energy not only powers the sun, but also balances the gravitational forces trying to compress it. This energy has far-reaching consequences. It provides the Earth with the heat and light necessary for life. It drives our weather systems, powers photosynthesis, and even influences Earth's climate over the long term. Understanding the sun is crucial to understanding the cosmic web. Various missions, such as the Parker Solar Probe and the Solar Dynamics Observatory, have been launched to study the sun's behavior. These missions provide insights into solar cycles, magnetic fields, and even the future of the sun. Although the sun serves as a vital node in the cosmic web, nourishing life on Earth and influencing our local space environment, it's just one example in a universe teeming with stellar diversity. Every star, regardless of its size or lifespan, plays a role in shaping the cosmic web. From the tiniest red dwarfs to the massive blue giants, each star is a unique knot contributing to the overall structure of galactic filaments. Stars are often classified by their mass and brightness and plotted on a graph known as the Hertzsprung-Russell diagram. This diagram shows the life stage of a star and gives clues about its future fate. Take, for example, a red dwarf, the most common type of star in the universe. They're small, cold stars, also called M-type stars. Often less than half the mass of our sun, they make up for their lack of size with longevity, burning for tens to hundreds of billions of years. Red dwarfs are frugal. They turn hydrogen into helium much more slowly than larger stars. This slow lifestyle allows them to be among the longest-lived objects in space. Now compare that to O-type stars, the rare titans of the stellar world. These stars are more than 15 times more massive than the sun and can be 1,000,000 times brighter. Yet they live fast, die young, often in spectacular supernova explosions. O-type stars dramatically end their lives. They collapse under their own gravity and then explode as supernovae. These explosions scatter elements such as carbon, oxygen, and iron into space, promoting the formation of new stars and planets. Star clusters are like cosmic nurseries, places where stars of different types are born. These clusters serve as nodes in the cosmic web, linking different regions of a galaxy and even connecting galaxies to each other through filaments. Computer simulations help astronomers understand how different types of stars contribute to the cosmic network. These virtual models can simulate billions of years of cosmic evolution in a matter of weeks, showing how stars serve as the building blocks of larger cosmic structures. So, we've already found out, stars are not eternal. They are born, live, and eventually die. The life cycle of a star is a cosmic journey spanning billions of years, a journey that plays a key role in the evolution of the universe and the structure of the cosmic web. The birth of a star is a spectacle of cosmic proportions. It begins in a nebula, a vast cloud of gas and dust. Gravity pulls these particles together, getting denser and hotter until nuclear fusion ignites. A new star is born. Once a star reaches the main sequence stage, it enters a period of relative stability. The hydrogen in the core turns to helium, releasing energy that balances the gravitational forces trying to compress the star. This is the longest phase of a star's life, and it's where our sun is now. But even stars, like our sun, must face change. In about 5 billion years, the sun will run out of hydrogen fuel. Its core will shrink, but its outer layers will expand, turning it into a red giant. This phase is the prelude to the final fate of the star. Depending on its mass, the star will meet one of several ends. Stars with less mass, such as our sun, will shed their outer layers, leaving behind a white dwarf. more massive stars may undergo a supernova explosion, resulting in a neutron star or black hole. These deaths are not in vain. The death agonies of stars scatter important elements into space, elements that will become the building blocks of new stars, planets, and even life. Thus, the life and death of stars is an integral part of the cycle of cosmic creation and destruction. The cosmic web, from individual stars to entire galaxies, is a complex network of interconnected structures. But what binds these galaxies together? What are the threads that weave the complex fabric of the universe? The answer lies in galaxy clusters. Galactic clusters are massive collections of galaxies bound together by gravitational force. They may contain only a few or thousands of galaxies and often span millions of light years across. Just as dark matter plays a role in individual galaxies, it also acts as an invisible glue in galactic clusters. Even though we can't see it, we know it exists, holding the cluster together and forming its overall structure. Within a cluster, galaxies are not static. They are in constant motion. Some of them may be heading toward the center of the cluster, while others may be on their way to its edge, under the influence of complex gravitational interactions. Sometimes these interactions can lead to dramatic events, such as galactic collisions. When galaxies collide, their stars, gas, and dark matter merge to form a new, larger galaxy. These events are crucial to the evolution of galaxy clusters, and, by extension, the cosmic web. But clusters are not the end of the story. They often cluster together to form superclusters, which are among the largest known structures in the universe. These superclusters serve as the main nodes of the cosmic web, linking numerous clusters and filaments. Understanding galaxy clusters is the key to unlocking the mysteries of the cosmic web. They serve as threads connecting galaxies, forming the paths along which matter and energy flow on cosmic scales. Having studied the colossal structures of galactic clusters, the threads that weave the cosmic web, we now turn our eyes to an even more mysterious phenomenon. What if there were actual threads, strings of pure energy that stitch together the fabric of the universe? These hypothetical one-dimensional defects in space-time could be the loose threads of the universe, remnants of the first moments after the Big Bang. Imagine the universe just moments after the Big Bang, a hot, dense state of pure energy. As the universe cooled and expanded, this energy condensed into matter and structure. However, not everything went smoothly. In some regions, kinks occurred, leading to the formation of cosmic strings. Cosmic strings, if they existed, would be unimaginably thin but incredibly dense. A string less than an inch wide could weigh as much as the Earth. They would stretch across the vast expanse of the universe, perhaps even from one end to the other. Because of their enormous mass, cosmic strings would exert a strong gravitational pull, affecting the motion of galaxies and even bending light. They could serve as cosmic highways, directing the flow of matter and energy through the universe. The search for cosmic strings continues. Scientists are using a combination of theoretical physics and observational astronomy to search for these elusive structures. If the existence of strings is confirmed, they may become the missing links that will help us understand not only how the universe is organized, but also why it is organized this way. However, let's return to structures of unfathomable scale. Superclusters. They are the gravitational anchors that hold together vast networks of galaxies and galaxy clusters. Imagine moving away from our Milky Way galaxy, past our local group of galaxies, and even beyond our local Virgo supergroup. You'll find a network of superclusters, each containing hundreds to thousands of individual galaxies bound together in a complex dance of gravity. The superclusters are unevenly distributed. They form a kind of cosmic skeleton around which galaxies and galaxy clusters are located. This skeleton gives the cosmic web the shape that defines the large-scale structure of the universe. Within the supercluster, galaxies and clusters are in constant motion under the influence of the collective gravitational pull of the entire structure. This dynamic flow of matter and energy is what keeps the cosmic network alive and ever-changing. Among the most intriguing aspects of superclusters is the presence of gravitational anomalies like the Great Attractor. These are regions with such a strong gravitational pull that they influence the motion of the entire supercluster, serving as the pivots of the cosmic web. Understanding superclusters is crucial to cosmology. They serve as the largest laboratories for studying the expansion of the universe, the distribution of dark matter, and even the mysterious force of dark energy. The observable universe is estimated by scientists to contain 2 trillion galaxies. And yet, what we can see represents less than 5% of the universe. Standing over the precipice of cosmic understanding, we are humbled by the scale and complexity of the universe. From the smallest particles to the largest galactic filaments, each element serves as a piece of the puzzle. Here we are, a pale blue dot, a mere speck in the cosmic web. Yet, it is from this vantage point that we've begun to unravel the deepest mysteries of the universe. Armed with telescopes capable of looking billions of light years away, we become not just spectators, but active participants in this cosmic journey. And each new discovery is a step towards the answer to the eternal question that prompts all of us to ponder: what other mysteries does the universe hold that we have yet to unravel? The moon has always been a beacon of mystery and wonder, but beyond its radiant beauty and folkloric tales, the moon holds secrets that have eluded us for centuries. Among these mysterious features is the moon's south pole, a region shrouded in perpetual shadow and intense cold, untouched and unexplored by any previous lunar mission. This is the story of Chandrayaan-3, India's daring journey into uncharted territory. Launched on a journey of more than 238,600 miles, Chandrayaan-3 embarked on a mission not just of distance, but of discovery. Its purpose? To unravel the mysteries of the moon's pole, a place where sunlight barely reaches, an area where the terrain is so treacherous that you have to wade through an endless maze of craters and rocks. Here, in this alien landscape, Chandrayaan-3 sought answers to questions that have puzzled scientists for decades. What lies beneath the surface of this mysterious region? Do earthquake-like tremors shake this silent world? And the most exciting question is whether water, the elixir of life, exists here in the form of ice. When Chandrayaan-3 ventured beyond Earth, it carried with it the aspirations of a nation and the curiosity of the world. Its primary goal was clear, yet challenging: to achieve a soft landing near the moon's south pole, a feat that had never before been accomplished. From the busy Mission Control Center of the Indian Space Research Organization, a team of dedicated scientists and engineers piloted this ambitious mission. Their expertise helped Chandrayaan-3 traverse the space void, overcoming the challenges of lunar orbit insertion and descent. The south pole of the moon is a landscape unlike any other. Here, the terrain is a patchwork of craters and mountains, many of which are shrouded in perpetual darkness. The challenge was not just to land, but to land safely in an area where the terrain is unforgiving and most slopes are quite steep. When the Vikram landing module separated from the orbiter, it began its descent. The landing module, equipped with advanced sensors and engines, began its perilous journey to the surface of the moon. Imagine a spaceship autonomously navigating a maze of craters and boulders in search of a patch of land safe enough to land on. The landing module's onboard systems were hard at work, analyzing every inch of the terrain below. Against this treacherous landscape, The landing module also struggled with extreme temperatures. The moon's south pole is a place of stark contrasts. The sun barely rises above the horizon, while shadows hide frigid temperatures that can drop to minus 382 degrees Fahrenheit. As the landing module made its final approach, the hearts in the Flight Control Center beat harder. Every second was decisive, every maneuver a test of human ingenuity and technological prowess. With a light thud, Vikram landed, marking an historic moment not only for India, but for lunar exploration in general. In the silence of the moon's south pole, Chandrayaan-3 began its mission of exploration and discovery. So, after the historic landing of Chandrayaan-3, a new chapter in lunar exploration began. The mission's goal was to maximize the study of the moon's characteristics, especially its elusive exosphere and ionosphere, and to establish the range of temperature variations just beneath its surface. The lunar exosphere, the thin layer of gases surrounding the moon, holds the key to the satellite's past and present. Unlike Earth's robust atmosphere, the moon's exosphere is so rarefied that it almost resembles a vacuum. The Chandrayaan-3 instruments, developed using the latest technology, are designed to measure the density and composition of this elusive layer. In addition to the exosphere, the mission delved deeper into the moon's ionosphere. This layer, formed by solar energy ionizing atoms in the exosphere, plays a crucial role concerning lunar communication and navigation. The Chandrayaan-3 measurements were designed to provide unprecedented information on the density and behavior of the ionosphere, which is important for future lunar missions and potential human habitats. Another intriguing aspect of the mission was studying the temperature variations just beneath the lunar surface using one of 4 instruments on the landing module, CHASTE, or Chandra's Surface Thermophysical Experiment. The temperature probe, immersed in the lunar regolith, was tasked with the critical mission of mapping the thermal profile of the lunar soil. The results of Chandrayaan-3 revealed a sharp contrast in temperatures. On the surface, during a lunar day, temperatures rose dramatically to 140 degrees Fahrenheit. While just 8 centimeters deeper, they dropped significantly to 14 degrees Fahrenheit, demonstrating the lunar soil as a potential thermal insulator. This discovery provided new opportunities for future lunar habitats, suggesting that the lunar regolith could serve as a thermal insulator, protecting astronauts from the moon's harsh extreme temperatures and harmful radiation. These studies were more than just scientific endeavors. They were stepping stones toward a future in which the moon could be a gateway to future space exploration. Mission results on the lunar exosphere, ionosphere, and subsurface temperature laid the foundation for understanding the moon's environment and its potential to support human life. Standing in the vast lunar landscape, Chandrayaan-3 was ready to detect a phenomenon that had not been observed for more than 50 years, a lunar earthquake. The mission succeeded in shedding light on one of the most intriguing and least understood aspects of the moon. The Instrument for Lunar Seismic Activity, or ILSA, a seismic instrument, was designed to detect the slightest tremors on the moon, and it did. Chandrayaan-3 detected what looked like a lunar earthquake, a significant discovery given that the last such observation was made during the Apollo missions in the early 1970s. Lunar quakes are fundamentally different from earthquakes. While Earth's seismic activity is largely due to the movement of tectonic plates, the Moon, which is devoid of these plates, experiences earthquakes for a variety of reasons. These tremors can last much longer than earthquakes, sometimes up to an hour, and their origin is a subject of scientific interest. The Chandrayaan-3 data suggests several possible causes for these earthquakes. One theory is a collision with meteoroids, which could cause shock waves that penetrate the Moon's crust. Another is Earth's gravitational pull, causing tidal forces that load the lunar crust. And finally, extreme temperature fluctuations on the Moon's surface can cause expansion and contraction, leading to earthquakes. These earthquakes are not just surface phenomena, they're windows into the Moon's interior. By analyzing the seismic waves, scientists can infer the composition and structure of our satellite's interior, which resembles a sonogram of the lunar interior. Such information is of great importance for understanding the formation and evolution of the Moon. The detection of a lunar earthquake by the Chandrayaan-3 spacecraft has not only provided a glimpse into the dynamic nature of our celestial neighbor, but has also opened up new insights into the geological processes that shape the Moon. To unravel the geologic mysteries of the Moon, Chandrayaan-3 carried out another exploration. Among the most intriguing finds was the discovery of sulfur, an element whose presence on the Moon has been shrouded in mystery. The Laser-Induced Breakdown Spectroscope, or LIBS rover, a marvel of scientific instrumentation, vaporizes tiny samples of lunar soil using high-energy laser pulses. When the plasma emits light, the spectroscope analyzes its wavelength, thereby revealing the presence of various elements, including sulfur. Sulfur on the Moon is a significant find. On Earth, sulfur is often associated with volcanic activity, raising questions about similar processes on the Moon in the past. Its presence could provide insight into the volcanic history of the Moon and the processes that shaped its surface. In addition to sulfur, another key objective of Chandrayaan-3 was the search for water ice, a search that's intrigued scientists for decades. Water ice on the Moon is not just a scientific curiosity. It's a potential resource for future human missions, offering water for life support and fuel production. Despite high hopes, Chandrayaan-3, like its predecessors, found no direct evidence of water ice on the Moon's surface. However, the lack of direct evidence is not a conclusion, but a clue leading to new hypotheses. One theory is cold trapping, in which water vapor can migrate to permanently shadowed craters of the poles, freezing into ice. The detection of sulfur adds another layer to this theory, as sulfur may be trapped with the water ice and released as a result of the breakdown of water molecules by high-energy solar radiation. The lack of direct evidence for the existence of water ice raises important questions. Is the ice deeper beneath the surface, shielded from detection by the insulating properties of the lunar soil? Or is its prevalence more heterogeneous and elusive than previously thought? During its exploration of the Moon's south pole, Chandrayaan-3 found more than just sulfur. The rover's LIBS instrument made the first ever in situ measurements of the elemental composition of the lunar surface in this region. In addition to sulfur, the instrument detected aluminum, calcium, iron, chromium, and titanium, each element reflecting part of the complex geologic history of the lunar surface. Further measurements added new details to this discovery, further revealing the presence of manganese, silicon, and oxygen. These elements, each with its own unique spectral signature, provided clues to the formation of the Moon and its evolutionary history. Studies of the presence of hydrogen, a key component in the search for water, also continue. The mission's discovery of these elements and the ongoing search for water ice underscore the dynamic and complex nature of the Moon's geology. Each discovery, each unanswered question, moves us further in our quest to understand our nearest celestial neighbor and prepares us for the next steps in lunar exploration. As the Chandrayaan-3 mission at the Moon's south pole opened a new chapter in lunar exploration, it also paved the way for the next ambitious leap, the Lunar Polar Exploration Mission, LUPEX for short. This joint venture between the Indian Space Research Organization and Japan Aerospace Exploration Agency is scheduled to launch no earlier than 2026. LUPEX plans to send an unmanned lunar lander and rover to further explore the South Pole region of the Moon. JAXA will likely provide the H-3 launch vehicle and rover under development, and ISRO will provide the lander. This mission represents a significant step in international cooperation on lunar exploration. The mission's goals are multifaceted. It will demonstrate new surface exploration technologies critical for sustained lunar exploration in the polar regions. Precise landings will be achieved by using a feature-matching algorithm and navigation equipment derived from the JAXA Smart Lander for Investigating Moon mission. The LUPEX rover will carry several instruments from JAXA and ISRO, including a drill capable of collecting samples from a depth of 5 feet, 1.5 meters. Finding and analyzing water are key goals of the mission, and the potential discovery of water ice could be a game-changer for future lunar missions. In parallel with LUPEX, ISRO's Chandrayaan-4 mission, designed to return samples from the Moon, is in the planning stage. Scheduled for launch by 2028, Chandrayaan-4 will consist of 4 modules: a transition module, a descent module, an ascent module, and a re-entry module. The ambitious goal of the planned mission is to return soil samples from the Moon, which will provide invaluable information about the lunar environment. The mission will involve complex maneuvers, including sample collection, docking in lunar orbit, and returning samples to Earth. Chandrayaan-3's innovative discoveries, from the detection of sulfur and other elements to the study of lunar earthquakes, have revealed new layers of the Moon's mysterious nature. These results provide crucial insight into the Moon's geology, its internal structure, and the potential for future lunar habitats. Looking ahead, the future of lunar exploration is promising. Missions like LUPEX and Chandrayaan-4, building on the legacy of the previous ones, will continue to explore the mysteries of the Moon. India's role in these endeavors is not only that of a participant, but also that of a pioneer. Such events truly inspire us to look beyond the boundless mysteries of the cosmos. The solar system has served as a reliable bulwark for life. But one day, humanity will have to leave its native Earth to continue existing. In recent decades, scientists have been desperately looking into the dim depths of space in search of a haven for life. So far, none of the exoplanets we've found have refuted the hypothesis of the uniqueness of life. But what if we're simply looking in the wrong place? Perhaps it's not the planets that hold all the answers, but their moons. In the mystical deep space, exomoons are unlike any other satellite in the solar system. The size of our Earth, these hidden giants have an amazing feature. Life can be found in their interior, many times more often than on ordinary exoplanets. Today, we'll dive into the mysterious, distant universe and try to discover why exomoons may someday change humanity. Let's go back to the very beginning of the history of exoplanet science. Since astronomy received a strong impetus only in the middle of the 20th century, scientists began to study the first exoplanets not so long ago. The first confirmed exoplanets were recorded in 1992. It was a group of Earth-mass planets orbiting the pulsar PSR B1257+12. Just 3 years later, scientists found the first planet orbiting the star 51 Pegasi, similar to our Sun. This was the birth of exoplanetary science, which is dedicated to the study of planetary systems outside our solar system, and, in addition, the search for places where human-like life could originate. Other exoplanets available in our visible universe didn't have to wait long either. In the following years, astronomers found several more exoplanets, until in 2009, the Kepler Space Telescope was sent to explore outer space. In just 5 years of operation, it was able to confirm about 715 exoplanets, with a size and conditions similar to Earth's. As of now, we already know about more than 5,500 planets outside the solar system, and the recently sent James Webb Telescope will likely to be able to show us even more distant planets. Further, in 2013, scientists were able to determine the planet's color for the first time, and a year later, they were able to record the magnetic field, and later, volcanic activity. Finally, in 2018, astronomers made a new, potentially breakthrough discovery. For the first time, a possible exomoon was recorded near the planet Kepler 1625b. While this may not seem like such an incredible discovery at first glance, exomoons open a new chapter in modern astronomy, not only as novel, hitherto unexplored space objects, but also as potential elements for supporting life on exoplanets and satellites themselves. Every year, knowledge about distant, dim exoplanets deepens, bringing scientists closer to a complete picture of the history of the entire universe. But how did the scientists manage to confirm so many planets in such a short time when it's impossible to take a photo of each one? Only 69 planets were found with images. The most popular method is the transit method, which you may already know. When an exoplanet passes by its central star, the same star becomes slightly dimmer, which reveals the presence of an object orbiting it. Although this method doesn't allow us to directly observe the planet, and may turn out to be just a glitch, it is currently the most effective of all. Exoplanet exploration plays a crucial role in all of astronomy and the future of all of humanity. Exomoons, as a new chapter in exoplanet science, may have great potential for the search for extraterrestrial life. However, despite this, exosatellites are of not much interest to current research. The main problem associated with the search for these exoplanets is their elusiveness to telescope radar. Although no scientists deny that some exoplanets may have satellites, it's an extremely difficult and, to some extent, even impossible task for our current technologies to investigate them. The transit method, or more precisely, the method of studying the shift in the spectrum of stars, can confirm an exoplanet. But a satellite orbiting it? Almost under no circumstances, unless, for example, the spacecraft is in the closest possible proximity to the object of observation due to a completely insignificant change in the brightness of the star. Thus, even the very first exomoon found by Kepler and the ones discovered later near the planets Kepler 1708b and Kepler 1513b are still not perceived as full-fledged proof of their existence, and therefore there is a possibility that it could be just some kind of technical error during the observation, which is not so far from the truth, since further observations did not yield any encouraging results. However, as in the case of the giant planet satellite Kepler 1625b, an exomoon can be seen if it is large enough. So far, the first hypothetical exomoon could be the size of the Earth and have a strange tilted orbit like Neptune's moon Triton. Such a huge size of a possible moon may become one of the most important elements in the further search for other moons. Thus, more than 20 exomoon candidates are currently known. All of them are gigantic. Probably at least for Kepler 1625b, it's the star around which it orbits. It is a red giant. This dying star can heat the moon's atmosphere, increasing its effective diameter and allowing scientists to detect satellites more often. However, perhaps right now, exomoons are not of too much scientific importance for scientists to invest a lot of resources in developing technologies to find them. At this stage of our science, exomoons don't seem to be a higher priority than other space objects, such as exoplanets. The satellites of distant planets are too complex to study and have a very high chance of a false positive result. Therefore, it may take months or even years of observation and analysis to confirm one satellite, when it seems more rational to spend this resource on exploring a planet with potential support for life, including human life. Of course, it is possible that exomoons may hide life in their interior, but alternatives in the form of rocky exoplanets like Earth are still of much higher importance in scientific circles. But we're going to focus on the exomoons themselves and try to investigate them. Is there any need to study these mysterious and hidden moons at all? In fact, these moons contain a lot of information for our complete understanding of the structure of the universe. But this will only be possible in the future, albeit not in the near future. The first thing that draws scientists' attention to even just candidates for exomoons is their size. The largest moon in the solar system, Ganymede, orbiting Jupiter, has a diameter of 3,273 miles, or 5,268 kilometers. But recorded exomoons can reach the size of the Earth, or even Neptune. Therefore, since such moons are even difficult to distinguish among exoplanets, it's incredibly exciting to imagine what moons might look like and what activity they exhibit. It's possible that some large exomoons have many of the features of planets, and that their study could overturn everything we know about satellites. Their similarities to other exoplanets, such as their likely geologic activity, bring us to the next important point for careful study in the future. and that is the support of life. We know that several moons of the solar system, such as Enceladus or Europa, despite their low surface temperatures and small size, could, hypothetically, be a haven for living organisms due to the presence of global oceans. However, what about the much more massive moons, which not only can support a dense atmosphere, but also have more access to building chemicals, both from the inside and outside? According to a study by the University of Washington, exomoons have more potential to support life than even exoplanets. They also have a habitable zone, although it's slightly different. But the main argument for exomoons as one of the most intriguing places for life to exist is the availability of several heat sources for them. The first source is the star itself, and the second is their planet. The moons are heated by the gravitational pull of the planet, which keeps the probable water in the interior of the moon in a liquid state. Moreover, heating from an exoplanet can stimulate geological activity, such as volcanic eruptions, creating enough gas inside the moon to maintain an atmosphere for a long time, and also bringing various crucial chemical elements to the surface. So exomoons are not as simple as they may seem. Perhaps the difficulty of finding them will be rewarded with a potential breakthrough in science. Finally, exomoons may become the necessary tool to study the formation of our universe. Thus, the analysis of exomoons near different stars and planets can reveal to scientists how space objects are formed, what factors are responsible for supporting life, and what the history of other planetary systems is in general. In particular, comparing the moons of the solar system with those of distant systems can give scientists an understanding of the specifics and conditions of their development, as well as an approximate value of the abundance of systems where complex intelligent life has developed. The Earth, hypothetically, may be almost the only planet on which life could have formed, at least in the visible universe. And any clues on exomoons with potentially higher chances of supporting living organisms can confirm or deny this. However, for now, deep exploration of exomoons is only a matter of the future. On the other hand, the James Webb Space Telescope mission will continue for several more years, so perhaps the hope of finding an exomoon for the first time in this decade is not going away. Nevertheless, since the search for exomoons is an extremely difficult and almost impossible task for our current technologies, exomoons are likely to become one of the drivers of technological progress. As we know, the transit method, or gravitational lensing, will not help to look for microsigns of the presence of exomoons, so this factor is already challenging scientists to modify or even create new technologies to capture such subtle objects. But this is a task for the near future. In the long term, both intriguing moons and exoplanets will require much more thorough analysis, including using images and samples of the atmosphere or even soils. So, if interesting candidates where extraterrestrial life exists are ever found, then comprehensive space missions are likely to follow, advancing human knowledge of the research focus. The only step we have left to take is to find such an exoplanet or exomoon. In 2026, the European Space Agency plans to send the Plato mission, which will continuously look at several areas in outer space to capture transiting objects. The mission will last for 6 years and may be the one to make this expected discovery. However, the benefits of exomoon search and exploration do not end with a technological breakthrough. Exomoons are very valuable natural laboratories located near various planets and stars. Analyzing the impact of these bodies on the moons will not only deepen what's known about the formation of planets, but also demonstrate to scientists the variety of conditions under which life can develop. For example, traces of bio or even techno-signatures created by civilizations on various moons can provide a clearer picture of the signs for the development of intelligent life, thus building more prioritized paths for future missions to the most likely planets or moons for aliens to live on. But for now, we can only wait for the moment when we find the first exomoon and begin a long but life-changing scientific and technological ascent. Exomoons, despite their invisibility and skeptical insignificance, may one day critically change everything known to the entire human race about our vast universe. Even a small observation can eventually become the main driver for revolutionary discoveries. Continued research will reveal more and more answers, and only by pursuing this knowledge will the cumbersome, mysterious cosmos one day become less confusing to us. But in the face of the vast universe, we must never lose our enthusiasm for learning, no matter how difficult and distant our desired outcome.